Okay, hello and welcome to this revision session on uh, quiz 1 for the course ML Foundations, which consists of weeks 1 to 4. So we'll be going over the contents of each week in sequence. So now Vishal will take over for week 1.
Yeah, thank you, ma'am. So here we'll. Am I audible, ma'am?
Yes, yes.
Yeah,
Yes,
thank
sir.
you. So we'll start with first week. So we'll just go through the content in a brief, and then we can discuss the doubts if you are having any. So let's get started. So I'll share my screen. So yeah. So the first week generally doesn't have much of the content, but we'll discuss whatever has been discussed in the first week. So in the first week, we have just went through briefly regarding the ML definition and all. So first of all, I'll try to define those things again. So generally, ML is machine learning is simply a study of algorithm that will improve automatically through the experience and by the use of a lot of data. So here there is a difference between that ML algorithm and that programming stuff. So in programming, generally we write some piece of coded and then we run that. But in MN, we generally develop an algorithm that will learn from a lot of data, whatever the data we are giving. Okay, so that will generally help us. That will generally help us. Like for example, you'd have been through the weather prediction example, or if you have to calculate the price of if you have to predict the price of the car or phone, or it is like any other stuff. So generally we use those ML algorithm to predict this all. Like in weather, if you are having the features like the value of the humidity or some other features like with climate conditions. So on those basis, we can predict the weather, and generally we predict the weather on those like stuff. So and those features only. So if we have to predict the rate of the price of phone, anything like that, if we are having some sort of data like observation, like 1,000 observation, and on on the basis of those 1,000 observation, we can predict the rate of the phone or the car. In that, we'll be using the features like, if you are predicting for the rate of the phone, we'll use the features like the camera, what like, and the screen, whether it's the type of screen or the brand and all. So these all can work as a features for us to predict the rate of the phone, or for if we have to predict the rate of the car, we can use some other features like how much mileage this car is providing, or the brand of the car, or you can say there are different features on those basis. And we can develop some algorithm to predict the rate of the car. Okay, why generally we use that? Why not that programming? Why not we are using that software, like simple software that is generally on the like simple programming we do, and why not we use those things? Because in ML generally it will help us to speed up the thing, or it will also enhance decrease the cost of the labor, human labors. So these are some of the important things, like important, what you can say, the reason that why generally we use the ML in spite of the simple programming steps and all. So many of the things can be done with the simple programming also, but the thing is you'll be needing a lot of like time to develop that, or to do the simple things. You'll be needing a lot of like coding stuff. So that's why generally we use ML in spite of a simple basic programming stuff. And in that part, in ML generally the most important thing is the data. So data is simply can be represented in this form. Like if you're having data with the features like this, will generally, like here there are like three observation. These are the observations. So like ABC is the vector, you can say first vector, or the first observation for any of the data we are having. And that label generally is the ground truth, or the value after calculating the with the help of these features. Like we are having three features in this example, features 1, 2, 3, and the value for the first observation is simply this is observation first, and this is second, and this is third. So for the first observation, like we are having A value for feature 1 and B for feature 2 and C for feature 3. And with the help of some algorithm, we can, or for example, if this is the simply data we have been provided to develop an algorithm. For that, if the value of that features 1 is A, and for feature B, feature second is B, and for feature third is C, then and if the label or the ground rule or the rate of that thing, whatever we are predicting, whatever we are predicting, the rate already has been given as alpha, beta, and gamma for 3 observations. So this can work as a data set. Not this one, like here we are having very less data, but yeah, if you are having data of like thousands and millions of data observation, that can work, that can help us in developing some algorithm. Okay, so and that we have discussed about the model. Also, model is simply the mathematical simplification of reality. I think so. Yeah, and that we'll discuss about the types of ML algorithm. So ML, like broadly, it has been classified into 2 parts: algorithm, and that is generally the supervised and the unsupervised learning. So unsupervised will be mostly the in the supervised learning you'll be having the label, what we can say the ground truth. So these things will be having already in the supervised learning, but in the unsupervised learning you won't be having the this label thing. So in the unsupervised learning, simply you have to the algorithm is simply understand from the data itself. If you don't have the label, that the final value or the final category has not been defined, okay, so those things will come under the unsupervised learning. And in the supervised learning, you'll be having the simple data, like mostly data, whatever you will go through will be under the supervised learning itself. So you will be having the ground truth value, you'll be having the final value on the basis of features. So those type of data will generally help us in developing some supervised learning. Okay, so this is simply a curve fitting curve fitting learning, you can say, this supervised one. And you have to, if you have to calculate the loss, this is the simply the loss formula to calculate the loss in the supervised learning. Okay, here n denotes the number of observations you are having. So on the basis of loss only we can predict, or we can say regarding the models. Like if you have example, if you have we have developed some 2 models like F and G, and 2 models, if you have calculated the loss for F and G, and we have in the final conclusion we concluded that the loss for F is less than the loss for G. So that can help us to tell us okay, which model is better. So here if the loss is for F model is less, then we can say okay, F is better than G. Okay, in unsupervised learning we generally calculate, in unsupervised learning we generally calculate the loss in this form. uh, okay, this is not for this unsupervised, this is for the, okay, so I'll discuss see, for in the supervised you'll be having this, I have written incorrectly. Okay, so in supervised learning you'll be having regression and classification problem. Okay, so regression generally help us to know, regression is simply you are having the inputs in the form of some features, and the output will be in the form of some values, continuous values. Okay, so that will come under the regression. So supervised, here it has been written by mistake, I've written this. But supervised learning, so you in the broadly the ML is categorized into supervised and unsupervised. In supervised learning, you'll be having regression and classification problem. So that in that supervised, you'll be having regression and classification. Regression problem, you'll be having some, the final data, the final label will be in the form of some continuous value. Like for example, if you have to predict the price of something, okay, price prediction or something, okay, like the price prediction of the house or anything in the form of some continuous value. If you are having the label in the form of continuous value, then you can say this is a form of regression problem. And the classification will be having some sort of like yes or no in the end. Like this can be rolled in the form of 1 or 0, or 1 plus 1 or minus 1, you can say. Okay, so this is generally the classification. Like for example, if you have to categorize the spam, the email you are getting into normal email and spam email, so this can come under the example of classification problem. Okay, so this is simply the loss to calculate, the loss for the calculation of classification problem. Okay, not for the unsupervised learning. So this is you can say this is different. This for if you have to calculate the loss for the classification, this is simply how many numbers, how many data that are mismatching. Okay, if you are like earlier, if you are having the data set and in that data set, if you already like, for example, it has been categorized into a spam email, okay, and your algorithm is telling, okay, this is not a spam email, okay, so this is a one misclassification, okay, so just you have to add all the misclassification and divide it the observation, okay, that will give you the loss. Here also, if you are having something, you have defined two algorithm, like for example 1 and 2, and then you are telling that the loss for first is less than loss for second, then you can say, okay, the first model is better. So whenever you'll be having a lesser loss, you can say this model is a better one, like compared to the other. Okay. So this was the totally supervised, like supervised can be classified regression and classification. Regression will be having the continuous in the label, and the classification will be having some sort of discrete like 1 or 0, or that is simply a yes, no type of question. Okay. And now we'll move to the unsupervised learning. Unsupervised will doesn't consist of in the unsupervised learning. If you're having some sort of data, and in the data the labels are not been given, okay, so this is simply the you have to, without the label, only with the help of features, whatever you have, like for example, if you are having thousands of observation with only features like 3 features, so you have with the 3 features, okay, so with the help of those data only, you'll be able to, if you are developing some algorithm that will categorize that. Unsupervised learning, you're having 2 or 3 types of, like you can do the dimensional reduction, also density estimation, or you can cluster the data set. So these things will come under the unsupervised learning. So yeah, somebody is asked, yeah, yeah, what?
Yes, so I have a question, quick question. So just a like a label question. You're talking about curve fitting, but basically what we have learned so far, either we are fitting a line or a plane, which is more like a linear. Yeah, there are some.
So that is also a curve only. Like if you will say, like if you are fitting a straight line also, okay, if you are having only 2 features, okay, in that case that will be a, we can say, a linear line. But if you will go to the more like if you will increase the dimension like 4 5, that will change into a curve, right? Are you getting my point?
Yeah. Got it. Yeah, okay.
Yeah. So in the unsuper, this was for the calculation for the loss for the classification, and this for the regression.
Okay. So if we talk about 3 dimension, we're still talking about a plane in 3 dimension, isn't it?
Yeah, in the plane also, yeah, in the 3 dimension also you can get one plane that will, if that is a classification, okay, in the regression also you can get some sort of plane, yeah.
Because if my y is a function of x1, x2, and x3, or let's say x1 and x2, and y is in a, let's say, 3rd dimension, essentially.
Yeah, you can get one plane that can fit. Yeah, that you there in the 3 dimension also you can get one plane. In the 2 dimension you'll get some linear line. Yeah, and but if you'll increase the dimension like 5 6 7, and then you'll start, you can't visualize those things, so that's why you'll generally tell, okay, curve fitting is the best way to say.
So we call it curve because I mean the functions that we're fitting are still linear, right? So where is that curve coming in? I mean, I understand the loss function is quadratic and all that, but generally people call it curve fitting because are there instances where our decision boundaries and everything is going to be nonlinear? That's why the curve comes in. Anyway, it's just a terminology.
Yeah, this is just a term to say that curve fitting. That's it.
Straight line is a special kind of curve.
Yeah, it's a curve only. A straight line is also a curve only, or you can say a plane is also a curve only. Yeah, so this is just a way of telling, okay, curve fitting.
Got it. Okay, carry on. Thanks. Carry on.
This radial descent, that is related to curve, no? That is a different type.
Let's not confuse gradient. That's how you find the solution. I'm talking about like what's the decision boundary. What you fit is actually a linear line.
Yeah.
Let's not confuse gradient descent.
A line is a curve of degree 1.
Yeah.
Yeah.
Okay, and if you move to other degrees, then you get parabola, hyperbola, every other thing, right? So it depends on degree.
Okay, got it.
Basically, in every term, we are doing curve fitting only, but of different degrees.
So in that case, I can fit a parabola or I can fit a line, right? So usually what we are seeing, if it is W transpose X, then it's a linear, right? Not a parabola.
So it depends on the data that you are having, right? So
if I have X squared term, yes. But if I have X, then it's a plane. If I have got X squared, then it's a, let's say, parabola.
Yeah, so a line is a curve of degree 1.
Yeah, okay. Got it. Thanks.
Yeah. Okay, thank you, Abhinandan. And then Yeah, so we were discussing regarding the unsupervised. So in unsupervised, we'll develop some algorithm if you don't have label. Okay, so in that case, you just have to understand the data, and then whatever has been asked, like if you have to cluster those data. So on those algorithm, we can cluster those data if we are having some sort of thousands of observation without label. So we can categorize it. So in this unsupervised, whatever we have studied in week first. Okay, so yeah, so this I'll discuss it later. But first, in the unsupervised is simply you have to understand the data and then build a model that will compress, explain, and group the data. So in unsupervised learning, we have learned mostly regarding the dimensional reduction and the density estimation the first week. So in the dimensional reduction is simply a technique of compressing the data and then simplifying those data. So here the encoder will generally there are two types of things like encoder that will help us to compress the data. If you're having some sort of thousand of features, so if you want if like thousand of features is also not much, but if you are having millions of features and all, so we can compress those features, and then with the help of decoder also we can undo those things. And so here the mostly the goal, our goal would be whatever we are doing, like if we are using that compressor or decompressor or the encoder and decoder, in the end the value whatever we have given the starting should match. Like that should be our goal, but that is it depends on the algorithm whether we are achieving how close we are achieving to that goal. Okay, so this is our important. This is the goal in the dimensional reduction, and we can calculate the loss with the help of this function. So all the laws, like three laws till now we have studied, like for the one is for the regression, one is for the classification, and one is for the this dimensional reduction. So these are like I put it star also. These are the like 3 or 4 concept that has been that is generally in the form of mathematical term that can be mostly asked in your exam. That is what I'll tell. And so yeah, and then the final thing that we studied in the unsupervised, the density estimation. So density estimation is nothing but just a simple estimation. Like it's a simple like a density estimation model generally takes in several samples from the random source and outputs of model that will assign a probability score to every possible instances. Like for example, here dimension density estimation is generally used if you are having some sort of like you are having like a lot of features. Okay, not features, if you are having some sort of observation, like I'm predicting if you are having like 500 MRI or 1000 of MRI, and if you have to predict whether this person is having some sort of like disease like Alzheimer. Okay, so if 500 observation, if we can increase the number of like the observation also with the help of density estimation algorithm. Like for if we are not able to, like 500 observation not much, because if we have to get more accuracy regarding the whether this patient will have Alzheimer or not. So what we can do, we can enhance the number of observation also. How can we do that? That will read in the ML techniques and all. But here I'll just give you some brief. Like if you are having features like 5 features, if you are having
Hello,
4
sir.
features. Yeah.
One small question. In this density estimation, the negative log, the log should be in base 10 or natural base.
Okay, if only log is written, just consider this as a base 10. If ln will be written, just consider that as a base with e. But if they've asked you some question, they'll tell you what's the base for that. Okay. But mostly if it's written in ln, that is with the base e, and if that is written log and they have not given anything regarding the base, then consider that as 10 base. Okay. So if we are having some sort of features like 4 features and we are having 500 observation and we have to enhance those things. So what we can do for the first feature, second feature of like 500 can work as some samples. Like we can get it some samples for features 1, and these samples will give us sort of like probability distribution. Like this will come, like for example, if this feature 1 has came with some normal distribution with some mu value and some variance. Okay. So with this value, mean value and variance value, we can get the normal distribution. That normal distribution we can get. Similarly, we can get for the features 2 and 3, 4, 5. Okay, for all the features we can get. And if we are having that normal distribution, so on the basis of those samples only we have developed the normal distribution. But now we can get a like a large number of observation from this normal distribution that is having mu some alpha and sigma as some beta. Okay, so now we can get, similarly we can do it for the features 2, 3, 4, and then we can like enhance the number of observation. So that will help us to like develop the algorithm in a better way. So yeah, so for in week 1, this is what we have been discussed. This is what we have discussed in week 1, and these 4 formulas are like utmost important, because if they ask you some mathematical like mathematical questions, so they'll ask you regarding to calculate the loss. They'll just give you 4, 5 of data set, and then will ask you to calculate the loss. So yeah, so this is what we have read in week 1. Nothing more, nothing less. So yeah, if you're having any sort of doubt, you can ask me. Otherwise, we'll move to the next week.
So what kind of questions will be there from week 1? Is it to calculate the loss functions for
Yeah, it can
different
come.
algorithms, or any other type of questions will be asked?
Whatever you have seen in the like the type of question, the assignments like practice and graded, those type of questions will be asked. Mostly the mathematical you should consider. So you should be able to calculate the loss for like 4 loss function we have done. Loss functions, whatever, like one for the regression, one for classification, and then dimensional reduction and density estimation. So those 4 you should be knowing. Like at least you should try to solve all the questions, the graded assignment, practice assignment. So you'll get mostly the similar pattern of questions in the exam.
Sir, I have a query. Like in practice assignment and graded assignment, there were no question on density estimation.
Okay, but in the lecture we have discussed, right? There was some sample, like we were having some sort of data, like samples, 4, 5 samples with one dimensional. And then with the 4, 5 samples, we have just developed some probability distribution function. And on those basis, we have calculated the loss, right? There were some example, I guess, in the lectures also.
Okay, sir.
Yeah, so those are pretty simple ones. So those you'll be able to calculate if there are any questions.
Okay, sir. Thank you, sir.
Yeah. Data test string. Okay. So in the evaluating, whenever we evaluate the learning models, whatever the models we have developed, the algorithm we have developed. So in that, if you are if you are having some sort of 1,000 data set. So in that 1,000 data set, we can just divide it into 3 like parts, like 60% for the test, training data set. So for this 60%, like 600 data set will help us, or 600 observation will help us to train that algorithm. Okay, and then we'll divide like 20% for the validation. That will help us to get the best model out of that. And then 20% for the testing case, whether this whatever the model or whatever the algorithm we have made is performing nicely or not, because we can't do that in the training data set, because on the training data set only that algorithm has learned all the things. So if you'll check on the training, it will give you 100% of accuracy. That's why it is generally do for the test data set, and on those basis we can develop some of the like curve and all, and then we can get the exact figure regarding the algorithm, how better our algorithm is performing. So this is what generally like till the here we have discussed. Anything else?
Sir, generally for the quizzes, what we've seen is generally the numerical values of the problems, of all the problems, are given in such a way that we have the minimum use of calculators. So, I mean, as long as I've seen in all the courses. But the mock for this course, there was quite a lot of calculation intensive numbers. So should we be expecting this kind of calculation? Because I end up making a lot of silly mistakes because of all those calculations. So...
Yeah. So from first week, you won't be getting much like questions that will consisting of a lot of calculation.
Yeah.
From the first week, it would be very simple. Like the data set will be also simple only. So and yeah, so you won't be getting much calculation problem from the first week. Like there will be question on the basis of like loss and all, but the calculation won't be that difficult to do that.
Okay, sir. Yeah, thank you, sir. because the mock had a lot of calculations. I mean, it took some time also to complete the mock.
Okay. But yeah. So from first week, like the calculation part won't be that difficult. That I can assure you. Yeah.
Fine, sir. Thank you, sir.
Yeah. Thank you. So yeah, then we'll move to the next week. So, Anamka ma'am, can you?
Sir, in case of probability calculation, how do you calculate the loss of log function in that calculator?
Log of loss
Probability.
function.
Yeah.
The probability will lie from 0 to 1, right?
Correct, sir.
So taking log, and why that is why we
but in the online calculator, which option we have to use? Because I am not clear about that option.
So that I have also not seen how, like, which type of.
It's the normal log you can use.
ln is also there. Ln of the log.
Minus log probability of that function, summation of that.
Log you can directly use, right? In the calculator, we generally have log. Okay.
Yes, we have.
And if you are having,
But sir,
yeah.
Sir, for log in base E, we have to use 10, base 10 or.
So what you can do, you can change the value, right? Like in the calculator, you would be having log and ln both, I guess.
Exactly. ln is base 10.
Base E, and this is
base E.
10. Yeah.
But the calculator which is showing over there is no log function, because on the online there is no log. I just want to know how to use that.
Log is available in
log is there in the
log is there in the scientific calculator. Yeah. Both log and ln both are there.
Sir, can you open the any week 1, week 0 activity, and there is a calculator function over there?
No, in the TCS and calculator.
In IIT calculator, that is not there. In scientific calculator, in those.
But online, that's why, because
the TCS will take your exam, right? In that calculator, somebody is saying that like the log and ln is present, so you won't be facing much problem.
Yeah, I've just pasted the link. In that you will have.
Portal also we have both log and ln.
Yeah. So yeah, you're good to go. Then you can calculate, and that also the value won't be that difficult to calculate. Like if you're getting 1/10, you can directly write -1, right?
Okay, fine.
All right, Vishal, I guess we can move on to week 2.
Yeah, thank you.
Yeah, thanks, Vishal, for covering week
So ma'am, in this particular question, that we have to take log base 10, right?
Yes, yes.
All right.
Yes. Okay, let me share my screen.
Okay, I'll just stop here.
And so the PDF that you showed, will that be shared?
Sorry, you're asking about week 1?
Yes, ma'am, week 1 PDF.
Yeah, we can share that, no problems.
All right.
Okay, so let's now move on to week 2 contents, and the topics that we are covering in week 2 are continuity, differentiability, linear approximation, higher order approximations, and then linear approximations of variables having, functions having more than one variable, and then there are directional derivatives. So these are pretty much the topics on which mostly questions can be asked from this week. So let's say you are given some function and you have to check whether it is continuous or not, or any other sort of question. Let's say the function is continuous and find these values. So these kinds of questions you can get from continuity and differentiability. And then linear approximation and its different variations, like when it's linear, the approximation is linear, or the approximation contains higher order terms, or the function for which you want to find the linear approximation has more than one variables, and then derivative in a particular direction. So these are the most relevant topics out of this week. So let's go over them one by one. So continuity, if you want to check for a particular function, you firstly would be interested in checking the continuity of the function at a given point. Okay, so that point will be given to you. Let's say the function is given and you have to check whether the function is continuous at a given point. Let's say x is equal to a or not. Okay, so what do you do for that? There are three things that you need to compute, and you have to check whether they are equal or not. So first you have to compute f of a, right? The function's value at the given point x is equal to a. That's one thing. Second thing is f of x with limit x approaches a minus, which means when you compute the function value, when you approach from left hand side, when the value of x is a little less than a. Okay, that's your left hand limit. That's the second thing that you have to compute. And the third thing is the right hand limit, which means the function's value when the value of x is a little more than a. So that's your right hand limit. When these three terms are equal, that means the function is continuous at the point x is equal to a, right? So that's the way to go about it. And in case you are asked whether a function is continuous in general or not, then in that case you have to make sure that the function is continuous at all the points in its domain. Okay, so in that case domain is expected to be given, and if you see that the function is continuous at all these points, then only you can say that the function is continuous in general. Okay, so that's about computing continuity. Next thing is checking the differentiability of the function. So and one more thing to note here is that the given function might have different equations based on different domains. Okay, so going back, when you have to compute the left hand limit, you have to see which is the right function equation when the x's value is less than a. That equation you will be using for computing left hand limit. Similarly, for computing right hand limit, you have to see which equation you have to use for computing right hand limit when the x's value is more than a. So we covered some examples in Solid Instructor. You can just refer to them to take some examples. Okay, getting back to differentiability, you have to compute two things to check whether a function is differentiable or not. Again, you would be given a point at which you have to check the differentiability. So here, basically, what we are interested in checking is that, let's say the point is x is equal to a, where you want to check the differentiability. So you have to see that the rate of change of function at left hand side is equal to rate of change of function at right hand side. Okay, which means when you approach the point x is equal to a from left hand side, what is the rate at which the function is changing? And similarly, when you approach x is equal to a from right hand side, what is the rate at which the function is changing? Now, how can we do that? We have to compute fx. So the rate of change of function, how do you check? So this is what you need to do. F of x minus f of a divided by x minus a. So this gives you the rate of change of function in that area, area which is given by x minus a. Okay. So that's the rate of change of function from left hand side. This is the rate of change of function from right hand side. If these two terms are equal, then you say that the function is differentiable at that point. So that's about checking differentiability. Now, next topic that is an important one in this week is linear approximation. And linear approximation broadly is finding the tangent to the function at a given point x is equal to a. Okay, so so what exactly is linear approximation? So let's say we have a function which has some degree, all right, which is let's say it's not a linear function, it has some higher degree. Okay, it's a non-linear function, and there's a point x is equal to a. We are given a point and we want to find the equation of the function which is linear. Instead of a higher degree equation, we are interested in finding an equation which is linear, which is of degree 1 around that point a. Okay, now how do we do that? Now imagine you are zooming in again and again at that point x is equal to a. So what you will get eventually is a straight line. When you zoom in enough, you will get a straight line. And the equation of that straight line is basically what is your linear approximation. Okay. And now how do we find that? So it's nothing but an equation of a straight line, which you might be knowing. So what is the equation of a line which passes through a point x1 comma y1? This is the equation. Y minus y1 equal to m multiplied by x minus x1. M is the rate of change of the function, basically the slope of the function, and y minus y1 divided by x minus x1 is precisely what is the slope. Okay, so this is the equation, and you can alternatively write it in this form. Now, what is the point here? Basically, what is x1 comma y1 here? So we want to find the linear approximation at point A. Okay, and the corresponding function's value will be f of a. So that means our point is a comma f of a. Okay, so what we want to emphasize here is x1 is equal to a, y1 is equal to f of a. When you plug this in this equation, this is what you get. And what do we replace m with? M is equal to f dash a, right? So we actually need the derivative of the function to be able to give the linear approximation equation. So when you plug in all these values in the straight line equation, this is what you get. Y is equal to f of a plus f dash a multiplied by x minus a. Now this is precisely what is your linear approximation equation. Okay, so this you need to remember this equation. L of x is equal to f of a is the point around which you want the linear equation of the function, which is not actually linear. Okay, plus f dash a, the first order derivative of function, multiplied by x minus a. So this is the equation through which for any higher degree function, you can get the simple linear equation, which will be able to give you the function's value in the vicinity of x is equal to a. Now, this is an important point. In the vicinity of x is equal to a means, so this is an equation which you can, this is the equation which you cannot generally use, but you can use only if you are interested in, finding the function's value around a. Let's say, a minus epsilon, a plus epsilon. So these are the points which are near a. For these points, you will get the correct approximation, like which will be close to the actual value of the function at that point. But if you go far away from this point x is equal to a, you won't be getting a good approximation. You'll get some value, but that wouldn't be a good approximation. So that's the main idea of linear approximation. So whenever there is a question on finding the linear approximation equation for a function, you would always be given a point. So that's important. Okay, now let's move on to a higher order approximation. So linear approximation means the function of degree 1. Now, can we get, let's say the given function is of degree 10, okay? And linear approximation gives you an equation which is of degree 1. Now, can we get an approximation equation of degree 2? That's the point here. So that basically is called a quadratic approximation as compared to linear approximation, and it will have one more term added to the equation, and this term is basically consisting of second order derivative of the function, which is f double prime a divided by 2 factorial, this is multiplied by x minus a square. Okay, now how did we get this? So moving on, you can also have a third order approximation, fourth order approximation, and so on. In general, this is what is the equation for a higher order approximation for any given function, and this comes from your Taylor series, if you've heard of. So Taylor series, basically what it does is it's a very interesting series equation which can give you some global information based on some local information. So if I can put it that way. And you will revisit this equation in week 7 when there is a gradient descent that is discussed. For now, this basically is the Taylor series, and you can make use of this Taylor series to get the approximation of a function of any order. So let's say you want linear approximation, you'll stop here. Okay. let's say you want quadratic approximation, you'll also go up to second order terms, second degree terms. If you want third order one, you will include this, and so on. So what we are doing here, this is very simple to follow as well. F of a plus f dash a, first order derivative, multiplied by x minus a, plus f double prime a, second order derivative of function, divided by 2 factorial, multiplied by x minus a of x minus a square, plus f triple prime a, divided by 3 factorial, multiplied by x minus a cube, and so on. So this is simple to follow as well. This equation you can easily use to find any order approximation for a given function. Okay, so that was the approximations for a function which is a function of only one variable, that is single variable function. Okay, in general, in any real life scenario, we come across functions which are functions of more than one variables, which are called multivariate functions. Now, how do we find linear approximations for multivariate functions is what we are looking at now. That is again very simple, and also a generalization of the equation that we just studied. Now, you know that when you have a function, multivariate function, you don't compute the derivative, you compute the partial derivatives. Okay, basically the gradient, which is a vector of partial derivatives. So if there is a function f, which is a function of two variables x and y, what you compute is dou f by dou x. Okay, that's the partial derivative of the function with respect to x, and dou f by dou y, which is partial derivative with respect to y. So these two things give you the rate of change of function in these two directions. Now, this is a generalization of that very equation that we looked at. So what we are doing is, so firstly, instead of x is equal to a, we have 2 points here that give us any point on the function, which is a comma b. Instead of x is equal to a, we have xy is equal to ab. Okay, so plugging in the values in the function, we get f of a comma b plus dou f by dou x at a comma b multiplied by x minus a plus dou f by dou y of dou f by dou y at a comma b multiplied by y minus b. Right, so it's also a similar equation, just that it's spread across the different variables that the function is dependent on. So this is the linear approximation of a function involving multiple variables. So if there are 3 variables, you will have one more term, which will be dou f by dou z. Okay, at a comma b comma c multiplied by z minus c. Okay, so you can generalize that way. So all right, that was about linear approximations. I hope so. You need it'll be good if you remember all these formulae, because they'll be.
So if I may ask a doubt.
Yeah.
Like, so we need to memorize mainly the 2 equations. That is first for the linear approximation, and the second is for like 2 multiple. Like we are given 2 variables and approximation using 2 variables.
Yes, and
right?
Also yes. So these 3. So I guess there are 3 formulae. Yes, you need to remember.
All right, we need to memorize the quadratic one also.
Yeah, so basically,
right.
If you remember this generalized equation, you can you can get any order approximation. So so it's actually simple. That's what I was trying to explain. It just follows a particular pattern. Every term is following a pattern. If you find it difficult, at the least you need to remember this, and then for quadratic, you add one more term. Yeah, to sum up, you need to memorize these equations.
And on the level of the quiz, would it be similar to the types of questions that we did in the practice assignment and mock test quiz?
Yeah, mock quiz you took a look at. So
yes,
yeah, more or less it will be same.
All right.
Yeah. So that was about linear approximation. Now, one more very important topic that is a part of week 2 is directional derivatives. Yes, you might get questions on this topic as well. I think there were questions in mock as well on directional derivatives. Now, what exactly this is? So we talked about gradient, which is a vector of partial derivatives. So let's say the function f is a function of x and y, 2 variables. What we compute is dou f by dou x and dou f by dou y. Now, what exactly is dou f by dou x? you can write it like this also, if you know. This is another representation of dou f by dou x. Now, what exactly this represent? This represents the rate of change of function with respect to x, while we keep y constant. Okay, so that's what it represents. Rate of change of f as we vary x while keeping y fixed, which means we are not moving at all in the direction of y. Okay. Similarly, if you look at the other counterpart, dou f by dou y, this tells you the rate of change of function with respect to y while keeping x constant. Okay, which means we are not moving at all in the direction of x. Now here, what we are interested in finding is the rate of change of function when you are allowed to move in both x and y's directions. So that's what is your directional derivative, which gives you the rate of change of function f if we allow both x and y to change simultaneously. Okay, now how do we tell how much we want to move in the direction of x, how much we want to move in the direction of y, because that may not be equal, right? So this directional derivative gives us the capability of moving with variable extents in the given two directions of x and y. So how do we convey that direction? That is done by giving a vector u. This is basically a unit vector that tells us how much you should move in x's direction, how much you should move in y's direction to be able to get the directional derivative of the function. So this u is actually, this u should be a unit vector. So in case you come across a question where you are expected to find the directional derivative of the function in the direction of that vector, and if that vector is not a unit vector, so the first step to go about is to first convert into a unit vector. And I hope you know how to do that. You divide the components of that vector by the magnitude of that vector, right? So that's how you get the unit vector, which gives you the direction. Now, what exactly is directional derivative? It's the weighted sum of the partial derivative. Okay, so this is what is weighted sum of partial derivatives. So what is this grad f? Grad f is gradient of f, which is the vector of partial derivatives. And then in order to get the weighted sum, you find the dot product with the unit vector that is given, and this is what you get. Sorry. So this is what you get. You multiply the dou f by dou x with the first component of the unit vector, and then you add up the second component multiplied with the second component of vector. So this is basically the weighted sum of the partial derivatives. Yeah, so that's about the directional derivative. These are the important topics that you can get some questions on, and I hope you went through the mock exam as well. So you can ask me if you have any questions on all these topics.
Ma'am, the ascent and descent.
Yes. So okay, were you there in the solve with instructor? So I actually have covered some 6-7 questions on this very thing. So we can briefly review that. So what exactly is we say gradient descent, right? So gradient descent basically tells you the rate of change of function where the function is changing the most in the negative direction. Okay, so there are two things, ascent and descent. So ascent gives you the direction in which the function is changing the most. Okay, so let's say you are given a function and you compute its gradient, which is vector of partial derivatives, that tells you the direction in which the function changes the most, basically increases the most. Okay, so this is a very important concept which is used in gradient descent algorithm. So gradient descent algorithm is basically used to get the parameters of a function which minimize the value of that function. So this is an important concept let's say when you study linear regression, where there is some loss function which comes in. I think in week 1 also you came across loss functions, right? So here in machine learning, it's all about optimization. Your motive is to get the theta 1 and theta 2, right? Weight vectors were there, right? In week 1 that you saw. So there is W1, W2, and you want to find the W1 and W2 which minimize the error, right? So this error has an equation. So let's say you plot that error function and you get some plot, right? Now, let's say you are at some point and you want to reach to the point W1 comma W2, which gives a minimum value of that error. Now, how do you automate this particular process? So you are at one point and you have no knowledge of any other thing, right? So what you can do is you compute the gradient of that function at that very point, and then that gradient tells you in which direction to move, right? So let's say you are at some point and you compute the gradient. That direction will tell you where the function is increasing the most, okay? But what you're interested in is moving to the direction where the function is reducing. So what you do is you move to the negative direction of the gradient. That's how you keep moving, again and again. Gradually, you reach at the point where the function's value is minimized, right? So that's the difference between ascent and descent. So gradient descent moves in the direction where the function's value is reducing, okay? And the opposite is ascent. Ascent is what is given by the gradient, right? I hope this differentiation is clear to you. So this is very important to be clear about. Actually, let me repeat again. So gradient of a function at a point tells you the direction in which the function is increasing the most, okay? Let me show you. One second. Is the screen visible to you where I'm trying to write?
No, ma'am.
Okay, one second. No problem. 1 second, let me reshare. Okay, is this visible?
Yes.
Yes.
All right. So I was saying that there's a loss function, right? Something like this. Let's say this is a loss function, and you're at this point. Let's say. So this loss. So let's say this is W1, and this is the function's value, the loss. So you want to find the value of W1 that minimizes this loss, and you are at this point. This is an arbitrary point. You have no knowledge of where to go. Okay, so this is an arbitrary point, and you want to automate this process of reaching at the point which minimizes the loss. So you are at this point, and you compute the gradient. So gradient will tell you the direction where the function is increasing the most. Okay, this is the direction where the function is increasing the most. But what you want to do is where the function is reducing the most. So you compute the gradient and then you move in the negative direction of the gradient, which is this one. And that's what is your gradient descent. That's why it is called gradient descent. On the other hand, gradient gives you the direction of ascent. So that's the difference which you should be clear about. Is this clear now?
So basically, when we get that vector of directional derivative, the gradient of f. So if we get a negative value, even if we get a positive value, we put a minus sign to get the descent, right, ma'am?
Yes. So
suppose
it's not about getting positive or negative. Whatever you get, you put a negative sign, and that will be your direction of descent.
Okay.
Yeah.
Okay, fine, ma'am.
So gradient is by default ascent, and if we take the negative, then it is gradient descent.
Yes,
right?
Yes.
Ma'am, I had a problem with
that we find out the gradient for a function.
Yes.
Right. So we find out the gradient of a function, and that gradient by default will give us ascent. So that
ascent,
is basically
ascent. So ascent means that will be the direction where the function is increasing the most.
all right. And if you want to find the descent, as you said, we just have to negate that equation.
Yes, exactly.
Right.
You have to move in the negative of that direction, and that will be the direction where the function's value
So how
will
do we do
reduce
that?
the
We
most.
simply use the negative of that equation.
Yes, simply use the
All
negative.
right.
That's all. Yeah. This concept will be revisited when you come to optimization part. But for now, this should be pretty much clear to you. The ascent and descent difference should be clear to you.
Ma'am,
Yeah.
I had a question for the continuity part, ma'am. In the graded assignment of week 2, there was a question wherein it asked that which of the following functions was continuous at x is equal to 1. And there was one function which was x square minus 1 upon x minus 1, which it said that it is not, I mean, the answer, I put it as continuous, but it stated that it is not continuous.
Okay, x square minus 1 divided by x minus
1.
So x at x is equal to 1, what do you get?
Ma'am, x is equal to 1. If I simplify that equation, I get it as x plus 1, right, ma'am?
You don't simplify because the function is actually x square minus 1 divided by x minus 1. So when you put x is equal to 1, you see your denominator is actually 0. So the function is divided by 0, which means the function is undefined at this point x is equal to 1. Okay. Now, when can you expand? Simplify is what is your question. So you can simplify when you are computing the limits. You know why? Because when you're computing the limits, you are actually computing the function's value not at x is equal to 0, but at some point, let's say, minus 0.000 something. So that's a point which is not equal to 0, but a little less than 0. So that is why this will never result in a divide by 0 error. Okay, I mean, undefined case. Similarly, when you're computing right hand limit, you're actually computing the function's value at a point which is little more than 0, so let's say 0.0001. So you can never get a divide by 0 issue again. So that's where, but in order to get an estimate of the function's value, you can do the simplification. Okay.
Okay, ma'am. Ma'am, so basically we should not simplify while finding out the continuity.
No, you should not. Yes.
But ma'am, when I put the same equation in Desmos, it does give me...
you zoom in enough. At x is equal to 1, you will see undefined there.
Okay, fine, ma'am. Thanks a lot, ma'am. Thank you.
Ma'am, in ascent and descent, you have mentioned that the direction is the ascent is the gradient and the negative is the descent direction. But you have not specified in that direction, we have to divide the magnitude to make it unit vector.
Yeah, so if you want to get the directional derivative, and you are, you're using, you're interested in finding that u, then you have to, divide by the magnitude of u. That will be your unit vector basically. Whenever you are computing the directional derivative, you will convert it into a unit vector. Okay. But he talks about the general terms. So whatever you get this vector u, right? I mean, you compute the gradient. This will not have magnitude 1. This will have...
No, ma'am. I am not talking about the unit vector. Like that in the questions, the direction of the steepest ascent of a function. It is in a function at a point.
Yes.
So in that case, we find the del f by del x and del f by del y of that function to get the gradient. And the direction, when you come to the direction, that is triangle of f divided that magnitude of f of individual gives us the direction.
Yeah. Yes. So whenever direction is asked from you, you should convert it into a unit vector form. So I think that question, I don't remember.
Yeah. In case of that ascent, if it is descent, then the numerator part will be the sign change and the denominator is same as magnitude.
Yeah. Yes.
Okay, fine.
So whenever in a question you are asked for a direction vector,
correct, ma'am.
It's a good idea to convert it into a unit vector form. Okay.
Exactly.
Yeah. So I don't remember. I think in that question the answer should be unit vector only. You may confirm that.
Yes, it's a unit vector.
Yeah. So convert it into a unit vector whenever a direction is asked.
Actually, you have explained only that gradient, if it is increasing in that direction, it is ascent, and in decreasing to minimize that error is the descent. But you have not specified that we have to convert into an unit vector.
Yeah, so we were talking about the general directions.
Okay.
But if you get a question and you're asked if you're asked a vector, directional vector, then I mean the general perception is that directional vector should be a unit vector. So I know this could be confusing, but that's why I'm clarifying it. Whenever you're asked a directional vector, convert into unit vector form.
Ma'am, if our ascent value is already negative, then that means the function is already decreasing in that direction. So then negating it won't be any help, right?
Okay, let's say something like this, right? So let's see over here. Again, same case. Let's see over here. Yeah, so gradient could be this. You're saying that gradient is negative, right?
Yeah.
Yeah, so okay, this is the direction in which the function is reducing. This is the direction in which the function is increasing. So gradient might give you this direction. And this is, yeah. So what is, sorry, what is the question? Your gradient is negative.
Yeah, if the gradient is already negative, then negating it again won't give us the descent value, right?
No, you have to negate always, because if you're getting a negative, no, this negative value is not for a function. This negative value, okay, you're saying that gradient is negative, so which means the two terms, some let's say alpha and this is beta. You're saying that this is negative, right?
Yeah, like
this is your gradient. So if this is negative, this will represent your ascent only. In order to get the descent, you will make it to be alpha and beta.
But
This is not. Please mind that this is not function's value. This is these are the points. I mean, this is a vector that gives you a direction. It could be positive, it could be negative, it could be a combination of both. I mean, it could be something like this. So that doesn't matter. This is a direction. This is not telling you function's value.
The gradient is a vector, and the negative sign in a vector, it doesn't represent the vector is more or less. It is the direction of the vector.
Exactly,
right?
That's what I'm saying. So it depends on the function. I mean, let's say the function is something like some complicated function. It could be possible that your first component is positive, negative, second is positive, or both are negative. That doesn't matter, because it's not telling you about the sign of the function's value at that point. Okay.
Okay. Yeah.
It's telling you about the direction. Let's say so this is the quadrant where both are negative. Let's say the direction is this one. Okay. If you take this point here, both x and y will be negative. This is not telling you anything about function's value. This is telling you about the direction. At any point, let's say this is one direction, this is one direction, this is one direction. So these are 4 different quadrants. So accordingly, you could have positive, negative, positive values in the directions that you get. Correct? So
Yeah.
it doesn't matter if you get this direction which is negative. All right. So any other questions, or we can move on to week 3. All right. Hi, Abhinandan, are you there?
Yeah, ma'am. So Amrita ma'am will take over.
Okay. All right.
So Amrita ma'am, you may continue.
Yeah, thanks, Anamika. Let me share my screen. Is my voice audible to everyone?
Yeah, ma'am. Yeah.
Okay, thanks. So good afternoon, everyone. So let us go ahead with the revision session for the week 3 contents. So the contents that you are learned in week 3 is linear algebra introduction. So the first topic is about the 4 fundamental subspaces, and followed by it, you are introduced to the orthogonal vectors and its subspaces, and after that projections, and finally have both least squares approximations and a simple example. So these are the contents for week 3. So let us first see the 4 fundamental subspaces. So whenever a matrix is given, so a matrix has rows and columns. So the first fundamental subspace is your column space. The second is the row space. The third one is the null space. And the last is the left null space. So when the matrix is given to you, see there are m cross n elements. So m is your number of rows and n is your number of columns. So the column space corresponds to the linear combinations of all the column vectors in your matrix. So if you consider each column in this matrix, the matrix has, this column has m elements. See? So that's why the column space is in a m dimensional subspace, that is Rn. So next is the row space. So if you consider this row space, the row space is the linear combination of all the rows in your vectors. So these vectors, row vectors should be independent of each other. So if you consider this row, each row has n elements. Can you see? So the rows have n elements. Therefore, the row space is an n-dimensional subspace. So the linearly independent vectors span the row space. Then when you consider this null space, why it is called as a null space of a matrix? Because this null space is a set of vectors x such that these vectors makes your matrix to be equal to the zero vector. So that is why it is called as the null space. So null space is a zero vector, that is, so the solution to this equation Ax equal to 0. So those vectors form the null space of your matrix. So since this is in your row vectors, that is why it is in Rn. Then left null space similarly is the solution for the equation A transpose y equal to 0. So therefore, when you transpose your matrix, your rows and columns are interchanged. Hence, it is an m-dimensional subspace. So those vectors which will make this A transpose, that is the transpose of your matrix A to be a 0 vector. So those vectors will span your left null space. So for example, let us consider this 3 cross 3. So there are 9 elements. So how do you compute your column space of this matrix? So first we use this Gaussian elimination process to form the upper triangular matrix of this matrix A. So how do you do this? So if you consider this matrix, let us consider the first element of the first column 1. So the elements beneath this element 1 should be equal to 0. So that is how we start our Gaussian elimination process. So what you can do is this second row. The second row can be given by R2 minus 2 times of this R1. And this third row, if you look at this minus 1, so hence R3 is simply R3 plus R1. Then you can get 0 in this element. So your reduction will be, the first row remains the same. And in the second row, you are performing R2 minus 2 times R1. So 2 minus 2, you will get 0. 8 minus 8, you will get 0. And 4 minus 4, you will get another 0. And R3 is simply R3 plus R1. Hence, minus 1 plus 1, you will directly get 0. And minus 4 plus 4 is 0. And minus 2 plus 2 is 0. So what is this matrix? So this matrix is your upper triangular form, that is your reduced form of your original matrix A. So here the first pivot element is in this element. So this is your first pivot element. So if in this matrix, can you find any other pivot elements? No, because all the other elements and the second and third rows are directly equal to 0. Hence, this is your pivot element. And what is the column space? So the column space is your column that is corresponding to this pivot element 1. So therefore, it is your first column. So the column space is your span of. So what is your first column? 1, 2, 1, minus 1. So that is the column space of this matrix. So here we do not have any other pivots. So therefore we have only one vector. The other two column vectors are the linear combinations of this vector, that is first column vector. So how we can get it? Some scalar multiplication, because we do not have more than one vector here. So the other vectors can be simply obtained by some scalar multiplication of this first vector. So
Hello,
this is how we find this column space of. Hello, yes.
Ma'am, when the matrix we transform it into the reduced row echelon form,
yeah.
For the column space, can we take the so there are two different ways, right? I mean, one is span from the original matrix and span from the reduced row echelon form. Is it?
No, that is.
Can I take the span of
for
100?
deriving this? That is used for this finding this row space of your matrix, right? The row space can be formed here. When you find this, yeah. So then only we have two methods. You know? So one is by finding this column space of the transposed matrix, or else your row space can be formed from your reduced row echelon form.
Okay, so for column space, we must have to take span of from the original matrix.
Yeah, from the original matrix. You reduce it to this upper triangular matrix form. And from there, you find the pivot elements, and the column vectors corresponding to those pivots are your column space vectors.
Okay. Actually, for some problems, I have taken the column from the row echelon form. So that's why I asked.
I see. So at that time, we use for row space, because row space is the unique space for finding this row space. We use that reduced row echelon form.
Okay.
Yeah. So for this problem, we can do two methods. So here, if you find this transpose of this matrix, then
sorry for interrupting.
Yeah.
If we get the pivot elements in first column and the last column, then the span will be of the original matrix column 1 and column 3.
Column 1 and column 3. See, in case if you have, say, 2 here, which cannot be further reduced, right? Yes, at that time, there are two. One possibility that you must do is, see, here in this second row also there must be some term here, say 3 or something like that. Then only this second row here, no? So the second row is also not equal to 0 fully. And this third row is also not fully equal to 0. See, at that time, this will be your pivot element here. Now the pivot element is here. So if you have complete zeros here and only 2 here, means you have to interchange these two rows. And that is for the upper triangular form. Anyhow, you will get only this third column as your answer.
But ma'am, if we interchange, we'll get the second column as the span, right ma'am?
No, see, if you interchange here, the second element is still 0, right? Your third element alone has the non-zero values.
Correct, ma'am.
Okay. At that time, your third column is still
Okay, fine. Yeah. Thank you, ma'am.
Yeah, thank you. So now, when you do this A transpose matrix, you will get 1, 2, minus 1, 1.
I'm sorry to interrupt in between.
Yeah.
Like in the very first question, when we find out the column space. So basically, we have to reduce the matrix to row echelon form or reduce to row echelon form.
To row echelon form, you can reduce.
So basically, that is that the first element should be 1 and all the elements below that should be 0, 0. Like the very first element of the column should be 1.
Yeah, very first element of the column should be 1.
Yes, ma'am. In case had it been...
See, here if it is not 1, if you have any other number, say for example 3 or so, that is also okay for upper triangular.
Okay.
And
Even
ma'am,
if you have
since
not,
we got
that
only
is
the
also
first
possible
row,
because you
we
are
are
reducing
taking
it
the
to
first column,
echelon
is it,
form.
ma'am? Hello, ma'am.
Yeah, since this is the pivot element, right? Yeah, hello, can you hear me?
Yeah. So just because we when we move to the row echelon form and we have two dependent columns and only one independent, we are taking only the first column, is it?
Yes, it is. We are taking only the first column because the pivot element
Because we have
here, no?
Yeah.
Yeah. See, when you say this is a pivot element, what it means, this pivot is corresponding to this first column. Can you get my point? See, if you have,
But if we take
general,
the second row, right?
see,
Second row will have only two elements, no?
see
In
here,
case if it is non-zero,
in the
like for some
second
other value.
row, see, okay, let me write another example. Say if you have, say, let this be 1, 4, 2. If you have some elements like this is your question, I think so. So if your reduced form can be also like this form, right? So at this condition, you have two pivot elements. Here there is one pivot element and here there is one pivot element. A non-zero number. So this is your, in the diagonals, we see the pivots. If you have non-zero entries. So at that time, so this is your first pivot, which corresponds to the first column. And this is your second pivot entry, which is the second column, this column.
Hello, ma'am.
So we need to mark the column space two columns, or only one column will mention, ma'am?
We make two columns. If you have two pivots, it means there are two independent columns. Yeah. The one thing is when you identify the pivot elements, we identify the corresponding columns which are linearly independent of each other. If you get all 0 rows, then it means this row is fully all zeros, right? At that time, this position of this row, if it is in the third row, then it means the third column is dependent on the other two columns. That is what the intuition behind this reduced matrix form.
Okay, thank you, ma'am.
Is it clear?
Ma'am, one question, ma'am.
Yeah, it is clear, ma'am. Thank you very much. Yeah.
Yeah. Okay.
Hello, ma'am.
Yes.
Hello. For that null space, we can take directly from the row echelon form, right? The column.
Yeah,
like,
the null space. Yeah, I will derive it and then explain.
Yeah,
the null
okay.
space
Actually, I confused between those two.
Yeah. Now next I will find the null space.
Ma'am, excuse me, ma'am, this row space, we can take the non-zero rows of this row echelon form, ma'am, matrix, instead of doing
this row space.
I remember, I think non-zero rows of this reduced echelon form, right? Can we take like
so
that?
if you, we can take. See, in this example, this form here, right? This itself is a reduced row echelon form because the pivot entry is 1 and we have no other entries. So this row, first row here, which is 1, 4, 2, this is also the row space of your matrix.
Oh, okay, ma'am. So, but we have to do this way. Transpose we have to do, and then we have to reduce. Both are equivalent, right?
Both will give you same answer. Only if the condition is this row space should be the unique basis for the row. Otherwise, you may get different answers while reducing it to reduced row echelon form.
Okay, I didn't know this because that's why I was getting different answers with the activity questions. Okay. Okay, ma'am. Thank you.
Yes. See, it happens only when such a matrix.
And this row space also we need to take the original row from the matrix.
That when it is a unique basis. Hello.
No, I'm asking like we are finding the row space, right? So again the row that is the 1, 4, 2. But here coincidentally it is same, but we need to take the original from the row from the original matrix, right?
Yeah, let me derive the row space from this reduction. Then you will get some clear ideas. Okay. So now, so let us finish this column space. I hope everyone understood correctly. So for forming this row space of the matrix, we shall first find this transpose of this vector matrix, that is I have written it here. So in this transpose of A, we are going to reduce this Gaussian elimination. So for that, your first row, we can keep it as such, 1, 2, minus 1. And taking the second row is simply 4 times your first row. So 4 into 4, that is equal to 0. So 8 into 4, that is equal to 0. And here, so since you are having minus 1 here, so 4 times of minus a plus 4, you will get 8. And in the third row, if you consider, it is 2 minus, sorry, I will write down here. So R2 minus 4R1.
Ma'am, it
and
is
here
4,
it
8,
is
minus 4. I think you missed the minus sign, ma'am, for the A transpose.
where? Here. So R3
Ma'am,
minus
the transpose second row should be 4, 8, minus 4.
A2,
2, 3.
So here 0, 0.
So below my ma'am, this is 4, 8, 4. In this row, the last element is minus 4.
Second
row on the A transpose.
I have written it wrong. Okay, fine. So then it is simple 0. Yeah, thank you. So now here R3 minus 2 times R1. So which will give you 2 minus 2 is 0 and 4 minus 2 is 0 and minus 2 plus 2, that is also equal to 0. So now see, now you should not take the row of the matrix. So now we have identified this pivot element here. So since it is column space of A transpose, you are going to consider this column of this A transpose as your row space. So that is why you should not confuse. So now the column space is 1, 4, 2. So if you look at the original matrix, this 1, 4, 2 is your row. Can you get my friend? So this is one way of computing your row space. So now to find, I think if you use this reduced row echelon form, you have to pick from this vector, from this form, because this is already a reduced row echelon form. So this 1, 4, 2 will be your row space. So now if you see, we have obtained both the row spaces same. So these two methods yield you same answers only if the row space is a unique basis of this matrix. Okay. So now let us proceed to null space of your matrix. So how do you find the null space of your matrix? So we already have this reduced row echelon form here. So now your null space is, you have to multiply this matrix by vector x, which is x1, x2, x3, and find the values for x1, x2, x3. So that is your null space vectors. So that is x1.
I just have one doubt in the previous question.
Yeah.
That in case pivot, the element, the matrix that we are getting after reducing it to the row equivalent form, it is that we have a pivot element in the very last column of the second row.
Here.
No, in the second row, in the second row, we have a pivot element at the last column over there.
Here.
Yeah. Yes, ma'am.
Okay.
So the span in that case would be what? 1, 4, 2 and
you're asking about this row 1, 4, 2, 1, minus 1, minus 4, 2.
All right. So we have to see the corresponding position of the elements in that particular main matrix, and we have to see the pivot element position, right?
Yes, we have.
Yes, we have to see the pivot element position, right?
Yeah, the pivot
right.
element position matters.
All right, ma'am. Thank you.
Yeah. So for null space of the matrix, you have to identify the pivot variable and free variables. So here x1 is your pivot variable and x2 and x3 are free variables. So free variables in the sense we are free to choose. So either one must be equal to 1 and the other is equal to 0. So here our equation is x1 plus 4x2 plus 2x3 is equal to 0. So here our x1 is your pivot element. So we cannot substitute any values for this pivot variable. So what we do is we are free to choose x2 and x3. Hence we set them to basis entries x2 equal to 1 and x3 equal to 0. So here what you will get for x1 then, x1 is equal to x1 plus 4 times x2. So x1 plus 4 plus 2x3, that is equal to 0 here. So that is equal to 0. So your x1 equal to minus 4. And another condition is you can set x2 is equal to 0 and x3 is equal to 1. So now your equation is x1 plus 4 times 0 plus 2 into x3, 2, that is equal to 0. Hence your x1 is equal to minus 2. So now you will get two vector combinations. So therefore, your null space will be span of two vectors where in your first vector x1 equal to minus 1, x2 is equal to 1 and x3 is equal to 0. And your second null space vector is x1 equal to minus 2, x2 is equal to 0 and x3 equal to 1. So this is your null space of your matrix, which is a span of two vectors. Then how do you find this left null space? So similar to this process, you will do with this A transpose matrix. Yes, hello?
Yes, ma'am. One question in the previous null space. Like how did you choose this basis 1, 0 and 0, 1?
Yeah, the basis we chose because we have two free variables, right? X2 and X3.
Yes, no, the value I'm talking about the
we
value
want
1 and 0.
and 1, 1, 0. Yeah, that is why I'm telling you. So that is here x2 should be there for finding this vector. No, the vector has 3 elements, right?
Yes.
So in these 3 elements, we first fix this first variable to be existing. So that is why we choose it 1. So this variable is existing. It is not a non-zero value. We have a free variable. That is why it is chosen to be 1. Only if you have x2 is equal to 1, you will have a value here. X2 is 1. This free variable exists, and that is why we have this 1 here. And we are choosing, okay, this x3 is not existing. Therefore, x3 equal to 0 in that vector. The vector should have 3 elements. No? So that is why we set them to basis entries for 1 and 0. And then we interchange it to 0 and 1.
Okay.
In
So
case if you have 2 pivots and only 1 free variable, yeah. So at that time, you directly put x3 as 1.
Okay. So ma'am, the standard, like whenever we have free variables, we take one of the free variables as 1, another as 0. Is that the?
Yeah. No, just to add on one more point to that, the reason we take 1 and 0 and 1 is because that's the identity matrix that we in the maths 2 studied the somewhat image and kernel. So this refers back to that topic when we were creating an image and when we were plotting it to planes. So if we could recollect from maths 2. The basis standard the 1, 0 and 0, 1 for 2 cross 2. That's it.
Ma'am, so we have to in case we have to find out the null space and we find a similar question. So for the independent variables, we have to assume it at 1 and 0 and 0 and 1 respectively, right?
Yeah, that is what we do.
Okay, that's what we have to remember, right? Or we can
that
assume
is what you
that we want.
remember.
All right, ma'am.
Yes.
Okay.
Yeah. Thank you. So for left null space, you consider this A transpose matrix is reduced form. So that is how we have this one. So the similar process. So you have y1 plus 2y2 minus y3
I'm sorry
is
to
equal
interrupt
to
again.
0.
In case of the left null space,
yes,
it is again we have to use the matrix that we use for the column space, row space, right?
Yeah, that is we want to use this upper triangular matrix form that is obtained from the transpose of the matrix.
All right, ma'am.
Yeah. So here there is once again there is only one pivot variable and there are 2 free variables. So you choose y2 equal to 1 and y3 equal to 0. So now your y1 will be equal to what y1 plus 2y2, that is plus 2, and y3 is 0, that is equal to 0. Hence y1 is equal to minus 2. And the second case is y2 equal to 0 and y3 equal to 1. At that time, you will get y1 plus y2 is 0. So minus 1 is equal to 0. So y1 is equal to plus 1. So your left null space is going to now be the span of two vectors. Which are, so for y1, y3 is 0. And y2 is 0, y3 is 1. So this is your left null space of any matrix. So I hope the fundamental spaces are clear.
Ma'am, if there is only one free variable, then also we have to put x equal to 0 and x equal to 1, right?
Yeah, when there is only one free variable, you will have only one selection. Yes.
Please continue.
Yeah, okay. So next is, this is a simple problem where if we given a matrix A and given a condition that is vector B, so how will you solve for this equation? That is, how do you find this Ax equal to B is solvable or not? So the condition is B should be belonging to this column space of this matrix A. So that is your condition to check. So how will you check whether a vector is in the column space of this matrix A? So you are going to augment this vector to this matrix and then reduce it to its upper triangular form. So 1, 1 and B1, 1, 2, B2, and minus 2, minus 3 and B3. So this was your general procedure. So what you do, you augment this vector to this matrix B and find whether you are able to get any non-zero rows. So the same Gaussian elimination procedure that is going to be followed here. So you can identify this first element is 1 here. So you will make the other two elements below this 1 to be 0. So this is simple. So R2 minus R1 we can do. And for R3, you can simply do R3 plus 2R1. So how will you reduce this form? So the first row will remain the same. In the second row, so 1 minus 1, it is 0. 2 minus 1, it is 1. And here you get B2 minus B1. Is that so? So we have to apply the same process to the third column also. And find the third one is minus 2 minus 2, it is plus 2, it is 0. And minus 3 and plus 2. So you will get minus 1. So here it is B3 minus B1. So now if you see the first pivot element, so here we have made both the elements to be 0. So now you can see that this third row can still be further reduced in terms of your second row. So that is R3 plus
B3 plus 2B1.
So okay. So B3 plus 2B1. So now your reduction process will be 1, 1 and B1. So the second row will be the same 0, 1, B2 minus B1. And your third row is 0 minus 0, 0 and minus 1 plus 1 that is equal to 0. So what is your condition is B3 plus 2B1 and plus B2 plus minus B1. So you will get B3 minus B2 and 2B1 minus B1. So therefore you will get plus B1, right?
B1 plus B2 plus C3.
Is that correct?
Yes.
So now, so this is your condition. So your condition is this B3 plus B2 plus B1 should be equal to 0. So that is your condition to this equation system of equations Ax to be equal to B to be solvable. Okay, because this row is not equal to 0, right? The first row is obviously not 0. The second row also we do not have any all 0 vectors. But if you make this third row to be equal to 0, this all 0 rows, then we can say that B is in the column space of the matrix A. Hence, the condition is B3 plus B2 plus B1 is equal to 0. So if you have any vector such that your third element in the column is simply the addition of the first two elements. So such vectors will solve this condition. Okay. So this is how you solve when you are asked to find the condition. Now the second topic is
Explain
orthogonal
the condition again. That
vectors.
how did we come to that condition? Like I
Yes,
understood
ma'am.
the
Please
way.
explain this once.
Yeah. Like how did we infer that what we have to do after the condition has come out like this?
Yeah, after the condition, so your condition is B3 is plus B2 plus B1 is equal to 0. So which means your B3 equal to minus of B2 plus B1. So that is the condition.
No, ma'am. I am asking that why is it that we are taking that particular
that is
position only as 0? Like if it is
that is
0,
because
then we are eliminating C as a dependent variable, right?
so that is why, because B corresponds to the column space of A. For this to be true.
Okay.
Because we cannot control these values, right? These are scalar values which we cannot control. But these are unknown values, right? B1, B2, B3 are unknown values. So that's why we are having some condition on them. That is what is given, right? AX equal to B is to be solvable. So this B has unknown elements, B1, B2, B3. At that time, we are trying to reduce this augmented matrix. So if you have all zeros in any of the rows, see, in case if you have a 0 here also, in case there is an all 0 row here also, at that time, you have two conditions. One is B2 minus B1 equal to 0 and this condition. So the only thing is we must get all 0 rows. So that is your condition. Why we know that all 0 rows condition? Then only it is satisfiable that B is in the column space of the matrix A. You got my point? So all 0 rows is needed for B to be belonging to this column space of A. For this vector to be in the column space of A. See, similarly, is it understandable? See, for example, if you see here, in this example, what you get is you have this all 0 elements in this final row, right? So this row, so this vector 2, 0, 0. Consider that this is your B1, B2, B3. So here all 0 row in the sense. So this vector column 3 is what is is a dependent on column 1 and 2. That is a linear combination of the vectors of column vectors of A. So that is why we say that when you have all 0 rows here, this vector, which is a column of this matrix. Imagine like that. This belongs to this column space of A. That is, this vector B is a some combination of your vectors, column vectors of A. If that is true, then we can solve this equation equal to B.
But this is not clear, man. How is it a combination of the column space of A, the B out here? Because your column is 1 0 0. So your B should be, if B belongs to the column space of A, then it should be some linear combination of any column space of A.
Any vectors of the column space of A.
Yes.
Yes.
So in this case, so here we are taking rows as 0.
No, that is the reduction condition, right? That is how you reduce the Gaussian elimination through that process. Don't consider it as rows as 0. It is a process of your Gaussian elimination.
Okay, but I did not understand the relation between these zeros in the elimination and the linear dependence of B on the column space of A.
It's like it's mentioned on the question. AX, we have to find the AX equal for AX equal to B. So X is X1, X2, and if we multiply it with A, then the third column will be 0. So as third column is 0, so B3 must be 0. Otherwise, it will make inconsistency.
Okay.
Am I right, ma'am?
Yeah. So if it is not in column space of A, then the system is we call it as an inconsistent system.
Yes.
If you do not get any all zero rows, it means say for you may be asked to give within a vector, you will be given with a vector, and you may be asked that will this equation be consistent or inconsistent? At that time, you just need to augment it with a matrix and try to find whether you get any all zero rows. If you do not get, then that is an inconsistent system, where we say B is not in the column space of A.
So now can we say another way of looking at it is that the rank of the matrix A and the rank of the augmented matrix should be the same, and then we can say that B belongs to the column space of A.
So the rank of the matrix A is,
and rank of the augmented matrix, which is A B, should be the same.
Oh, the augmented matrix you're asking. Yeah. So if this A has rank 1, and after augmenting, if it is still rank 1, then that means these two have same rank in the sense they have only, the first column will only be the pivot element, pivot column. That is also one way of expressing.
Okay.
If you if you get different rank, then it means
then it's not solvable.
It is not solvable.
Right.
Yeah. Yeah. So let's move on to the other topic, that is orthogonal vectors and subspaces. So here, what is your orthogonal vectors property? Say if you have two vectors, say x and y, your orthogonality is the dot product of these two vectors should be equal to 0. That is what is the orthogonality property. So now how do we relate this orthogonality with the subspaces? So if you say that two subspace, that is a row space and null space, are orthogonal to each other, that means every vector in the row space of the matrix A should be orthogonal to every vector in the null space of the matrix A. So that is why we call them as orthogonal complements. So from this picture, we can easily remember that your row space and null space are orthogonal complements, and the column space and left null space are orthogonal complements. So the dimension gives you the rank of the matrix. So here, if you consider this property, that is the rank nullity theorem, which tells you that the rank of the matrix plus the nullity of the matrix A is equal to M. So what dimension of this row space plus the dimension of your left null space is equal to M. So that is, you can relate from this equation. So R plus M minus R, that is equal to M. And here R plus N minus R, that is equal to N. So this picture gives you a simple remembrance for relating the orthogonality of your subspaces. Okay. So now let's go to projections. So for finding the projection of a line vector onto another vector, how do you do that? It's simple. If you are having a vector A, so this is a vector. Now I'm having one more vector B. I'm going to project this vector B onto this vector A. So this projection is given by this P. So that is some scalar multiple of your vector A. So we have found this x hat to be equal to A transpose B by A transpose A multiplied by this vector A. So this is your projection formula that you use to find the projection of any vector onto another vector. So from this formula, what you can do is, instead of having x hat A, you can also write A into x hat. At that time, you will get A into A transpose B by A transpose A. So that you get your projection matrix. That is projection matrix of vector A. So these are the two main formulas that you need to remember for finding the projection. One is the projection formula of a vector onto another vector, and the projection matrix of a vector. And this projection matrix is found to be symmetric in nature, and also the square of projection is also equal to the projection. That is, it is understandable, right? You are already projected onto this vector, and making another projection, which will result in the same value. So that is why P square equal to P, and this P matrix, if you find, that is a symmetric matrix. Okay. This error is, since you see it is a perpendicular to, that is why we have this 90 degree. So this error vector is obtained by subtracting your vector from this projection, that is E equal to B minus P. So a simple example. So if you have a vector A that is minus 3, 1, 3, minus 2, 1, how will you find this projection matrix of vector A? It is simple. You consider this matrix vector A and multiply by its transpose. So you will get, since it is a multiplication of 4 cross 1 into 1 cross 4, you will get a matrix. So I can simply multiply, right? Minus 1 into minus 1, 1, minus 1 into 3, minus 3, minus 1 into minus 2, 2, minus 1 into 1, minus 1. So likewise, if you do this first element, that is first minus 1 into with all these independent columns. So that's why you get a 4 cross 4 matrix. So if you, next is you have to do A transpose into A. So here you will get a scalar value since you have multiplication of 1 cross 4 with 4 cross 1, that is equal to 15. If you multiply these values, you will get a value of 15 here. So once you have these two values ready with you, then simply the projection matrix is this value A transpose. This projection matrix, you can find that elements are symmetrical. So you can see minus 3, here 2, 2, minus 1, minus 1. Hence, we call this P as a symmetric matrix. Okay. So once you have obtained this projection matrix, if you are given with any other vector, so you have this, initially you had the vector A, you find the projection matrix. So if you are asked to find the projection of any other vector onto this matrix, it is simply the multiplication of your projection matrix with the vector B. Hello? Is anyone talking? So when you have this projection matrix, you simply multiply with the vector to get the projection of that matrix. Okay, so this is how you do projection of a vector onto another vector using this projection matrix. The last topic is least squares approximation. So why do you have this least square approximation? See, oftentimes what happens is this equation AX equal to B has no solution. So why doesn't have no solution? That is because there may be too many equations. Why? Because there may be more rows than the number of columns. For example, if there are more number of data but less number of features, you consider such scenario. So that is why you have too many equations where there are more equations than unknowns. And because m is greater than n. So at that time, what happens is your columns will span only a small part of your n-dimensional space. Because there will not be much of the columns to span the space. At that time, this error, that is E equal to B minus AX. That is what is your equation, right? AX equal to B. From there only we derived this one. So this error, which is should be equal to 0, but it is not equal to 0. So that is what you approximate using least squares method. So we have this approximation equation that is we solved in class, that is using your projections we solved the equation, that is A transpose A into X hat equal to A transpose B. So this X hat will give you this linear approximation, that is this X hat is equal to your slope and intercept of the line. That is what is your
Hello, ma'am.
linear approximation. Why we get a line? Because
Hello,
it is a
ma'am.
linear approximation. That is why we get a
Hello.
line. Hello. You can ask any questions.
No, ma'am. Someone kept him unmute. So can you mute him or her?
Is it?
Some noise is coming.
Yeah, I muted.
Okay. Thank you.
Sir.
Yeah. So, for example, it is considered one simple least square approximation. So here you consider this X and Y coordinate system. There is a X is your independent variable, and this y is your dependent variable. So therefore, you are going to find the
Swaraj De Dulha becomes the Nawab of Bengal.
Someone is talking, I think, again.
I'm muted again.
Yeah, thanks. Okay, thanks again. So now our job is to find a best fit line for representing this data points. So it can be this line, or it can be this line, or it can be this line. So which line is best? That is what is being found from your least squares approximation. So from this figure, you can find the x points and y points. So here we are going to have the augmented coefficient matrix A. So the coefficient matrix is formed by this column of x and the column of ones. So this is for finding the slope, and this is for finding the intercept. That is why we have the ones in the right hand side. If you interchange this ones and x, then you will get in the solution, the first value will be intercept and the second value will be the slope. Okay. So this is your coefficient matrix. This is not any simple matrix. This represents your coefficient matrix. And after you form this matrix A into A transpose, you can find this A transpose into A as this matrix value. So that is, you have this A transpose and you multiply with this A. So you will get one matrix here. Similarly, you have this B as your vector of this Y. That is your dependent variable. So this B is here, you have A transpose. So A transpose B will give you 49 and 14. So you do normal system of linear equation solving. Then you will get this best solution to be in 0.7 and 0.7, where this 0.7 corresponds to slope, and this value corresponds to your intercept of the line. Why it is important? Because when you form the line equation here, this is y is equal to mx plus c. If you have any different value and if you interchange the value, then your future prediction will be different. So this is your line equation. So the best line equation is 0.7x plus 0.7. That is we obtained through our least squares approximation. So if any future value of x is asked, say for example, I'm giving you x equal to 7 and asking you to find what is your y value. So that y value is equal to what? 0.7 into 7 plus 0.7. So that is somewhat lying on this line here. For example, that may be say 5.3 or something like that. So that is why we use this least square approximation to predict any future value that lies on this line. So that is why we call this line to be a best fit line, which has the minimum error. So that's all. These are the topics in week 3.
Can you please go to the previous slide?
Yeah.
Previous linear. Could you please once again explain the matrix A? How did we got that?
This matrix A.
Yes.
Yeah. So this matrix is a coefficient matrix. Okay. The coefficient matrix is for this slope and intercept. That is our solution here. X hat. So the first column is your values of your x. That is the independent variable. So from the chart here, your x is what? For the point A, x is 1, and point B, x is 2, point C, it is 3, and D is 4, E is 5, right? So 1, 2, 3, 4, 5. So that is your first column, 1, 2, 3, 4, 5. It is your x value here. And you're augmenting with a column of ones. Why? Because that is your representation for this equal to mx plus c, right? That is your linear equation value, right? So this A is a coefficient matrix. So the first is belonging to this slope here. And the second one for this intercept. That is why we augment this one.
Ma'am, why we are taking one values on only?
Could you please explain this part again?
Because this coefficient is 1 right here. This value is 1, no?
Ma'am,
1
there is a
times the C.
question. There is a question in chat also.
Okay.
So if we take this 1 as first column, the only difference will be the exchange of the slope and intercept. Ma'am, can you explain that?
Yeah. See, if you consider this one here, that is also actually allowed. You can also use that representation. I think this is what is the question is, right? So instead of forming this coefficient matrix, if you have AS here, then your line equation will be y equal to C plus mx. Okay, then that is your x hat, that is the solution for this equation, right? This solution here, this is your solution, right? X hat is your least square solution. This solution vector that is arrived from this equation. So in this solution equation, this theta prime hat corresponds to your slope and theta double prime hat corresponds to your intercept. If you interchange this 1 and 0 here, if you do this interchange here, at that time you need to interpretation of the values result alone will be different. Can you understand that? Do you understand why we have this
Explain
one
this
here?
type of question again from scratch. Like, what are the steps that we follow?
Yeah, this is the method to follow. See, for example, let me come from this slide, okay? See, if you are given with some data points, it may be the data points, you may be given in a tabular format also. See, 1, 2, 3, 4, 5. That is x, and y is say 2, 1, 3, 4, 4. Okay. So instead of this figure, you may also be given with the table format of x and y. So here x is your dependent variable and y is your independent variable. That is, you are going to approximate this y from this x. That is, you are going to find a model such that you can represent this y. That is what is least square approximation is, right? Now how you are going to find? So that model is your line. That is y is equal to Lx plus c. Okay, so this y is this y. You are going to find an approximation of this best line. How we are going to find this? We are going to find this using someone is talking. So now in order to find this one, right? This one we are going to approximate using this our least squares approximation method. That is A transpose A x hat equal to A transpose B. So for this A matrix, so A is a matrix that is formed from this coefficients of this line. So what are the two coefficients? What are the two parameters of this line? First is your slope and the second one is your intercept. Slope is, I think you know, this is your slope, the value of dy by dx, that is your slope, right? And this c is your intercept. Intercept is the place where your line will cut this y-axis. That is your intercept. So these are the two parameters of the model, and the coefficients are.
Ma'am, then why we take 1 here for the as a second column?
The value for your slope and the value in coefficients of the slope is 1, right? Can you get me? So for solving this, we are making this matrix A to be, I'll just write it as here values for x, that is 1, 2, 3, 4, 5. And this coefficient of your slope intercept, that is 1, 1, 1, 1. So this is how you form this coefficient matrix. So once you find this coefficient matrix, rest is simple. B is only your y value. Directly you can write 2, 1, 3, 4, 4. That is your y value. So now you will have the values of this equation A and B. So you can first find this product A transpose A and this A transpose B. And the rest is solving the equation.
Ma'am, in case of normal linear equation, if it is a quadratic equation, the line is a quadratic equation. Then in that case, our matrix is first column is x square, then x, then the coefficient 1.
Yeah, that is polynomial regression, right? That is not linear regression. Linear is
for this model,
best fit is 1.
If we need a best fit line, whatever.
Yeah, best fit line at that time, see here. Yeah.
So that in that case, our matrix A will be changed in the form of x square,
yeah, correct.
x, and the solution, the solving is remains the same. Is this the correct?
Yes, the solution is the same.
Ma'am, I still don't get how the 1 is the intercept here. as you took 1, 1, 1 for the on the second column.
Yeah, that is the coefficient of your intercept, right? So what is this coefficient of your x? Coefficient of x is m.
Can I explain
What
for that
is
why it
the?
is one, why it is coming one?
Yeah,
Can I
yeah, you
explain?
can explain.
Okay.
Yeah, you can explain.
So for this, this you can write y1 equal to m x of value is 1 and y2 is some constant mx c 0 and y3, that's the y value y3. So in all the cases m is constant and taking the value of x and c is always constant. When you convert into a matrix, it is coming 1 1 1 and we multiplied with m and c. Hope that clears.
Yeah, this is a coefficient of the parameters of the model. Simple. You just see like this, no? Your model is y equal to mx plus c. Your matrix A is the coefficient matrix. Coefficient matrix for what? Coefficient matrix for the parameters m and c. Did you get my point?
But
That
here
is why we have one here.
we have okay, so we are taking C as 1 for all.
Yeah, see here, no, not C is 1 for all. It's not like that. It is this coefficient I have written here, right? 1.
I think if you just write down the system of equations once in the form of matrix, then it will become clear.
See here, it is 1 here. Can you see this 1 here? So what is this 1? This 1 is your coefficient of this C. Yeah. This is the
Just to
intercept.
make it C, instead of C, we are considering 1 into C. That's why 1.
Yes,
Yeah.
it's 1 into c, right?
Okay. Okay, I got it. Thank you.
Ma'am, I have a conceptual doubt.
Yeah.
Why do we multiply
We are
by
going to
8?
solve this. Hello, is it clear?
Yeah, the one part is clear, I guess. I wanted to ask, why do we multiply by A transpose on both the side in the formula? Actually, I didn't get the hang of the formula. It's A transpose A.
Yeah. See, that is from your projections, right? From the projection of the line, then onto the line, onto the column space. Do you remember that projections formula? So what is your projection? Projection is A transpose B by A transpose into A or A transpose A. You project a vector onto this another vector. From there only we use this, derive this least squares formula. It is not like multiplying this A transpose on the both sides. See, here like this, no? It is not like multiplying both the sides. What is your projections? From projections only we derived this least squares method.
Okay, yeah, got that. I missed this slide. Got it.
Yeah. Okay. Yeah. Okay, so if there are no more questions, I think we can move on to week 4.
Yes, ma'am. We can move on to week 4.
If you have any questions, yeah, thank you.
Hello, ma'am.
So let me stop sharing. Yeah, hello.
Yeah, a small conceptual doubt. Just add on to Chandak that so we can find a similarity like from the projection matrix. We want to project the B onto A. So we are constructing the projection matrix of A. and when we are multiplying the B with A, we getting the projection. So when we multiply the matrix in the left side of a column vector, so so what we got that is a vector on the first matrix. So what a matrix does, like what is the concept, like what is the significance of this, a matrix multiplication here?
No,
And
actually,
like
why
the same,
we...
and ma'am, the similar thing in the least square also, like a theta equals b. When it is not fitting the points, we multiplying the a transpose, and it is making the like magic. So what is the like the interpretation physical significance here of the matrix multiplication?
Misunderstanding.
Ma'am,
See,
ma'am, we
why
are covering that part in lecture 1 of week 4.
Yeah, you can finish this week 4.
Hello,
And
sir.
if you have
Hello,
any...
Can I
sir.
stop sharing? Will you share?
No, you continue, Abhinandan. After this, your lecture, I think he may understand that part.
Yes, sir. Yes, ma'am. No problem.
Yeah, so one simple understanding I will give you is why we go for projection is we are going to project that point onto the line. So that is why we relate these projections. Where point that do you remember that point A? So we have that point A is getting projected onto the best fit line. So that is the main concept here.
And can we have interpret this as that we want a solution in the column space of A? So that's why we are projecting the vector B on
No,
it.
see, that is difficult. That is finding a solution in the column space of A is difficult because there are more unknowns. That is what I introduced you. The system of equations will have more rows than columns. So
Right.
it is difficult to find this B that is belonging to this column space of A. So that
So
is
when-
how we derived this least squares. We cannot find such B in the column space of A.
So won't
So
the
we are just
projection help?
similarly adding up all the projections.
Yeah.
That is what the error is.
Okay. Oh, right. Got it.
Yeah. So we are trying to minimize this error.
Right, ma'am. Right.
Yeah. Okay. Yeah, I think we can proceed to week 4. So after week 4 is complete, ask doubts in week 4, and if you have doubts in week 3, we can have after the sessions over.
Yes, ma'am. It's
Abhinandan,
better.
I think you can continue with week 4.
Okay, thank you, ma'am.
Yeah, thank you.
Yeah, so in week 4, lecture 1, linear and polynomial regression is covered. So there feature matrix is introduced, right? So what is a feature matrix? Actually, we have covered all these things in week 4 live sessions, the 2 sessions, all the concepts were covered. So I'm repeating it again. So a feature matrix is something, so consider a problem. Suppose we want to predict income of a person based on these 3 criteria: his age, education, number of years of education, and experience. Okay, so all these data which you are collecting as age, education, and experience, this is one example. Okay, this is one observation. As Vishal said, this is one observation. Similarly, observation 2, observation 3. Now these 35, 15, 3, 45, 15, 8, 35, 16, 5 are represented as columns and are called feature vectors. So when we stack these feature vectors together, we call it a feature matrix and we represent it as A. So a feature matrix is nothing but these feature vectors stacked as transposed. Okay, and what is this income? This income is nothing but the output label that you want to predict, and it is represented by Y. Okay, so in this case, X1 is 35, 15, 3, X2 is 45, 15, 8, and X3 is 35, 16, 5. And feature matrix is formed by transposing these feature vectors. And output label vector is Y. Next, suppose we want to fit a model So the predicted model, when we are saying it's a linear regression model, our model is something like this: theta naught plus theta 1, x1 theta 1 plus x2 theta 2 plus x3 theta 3. So see, x1, x2, x3 are the features. Like in our example, the features are age, education, and experience. And theta naught, theta 1, theta 2, theta 3 are the parameters which we are basically estimating to find any model. So in linear regression case, our model looks like this, the predicted model. So I'm representing y hat as the predictions, and the model is this whole equation. And the estimates, basically finding these estimates is nothing but finding the model. So every estimate will have some error. So error in case of linear regression model is given like this. You subtract the actual from predicted and then square it. Okay, so this we called squared error. So simply for any ith example, suppose the prediction is y hat I and the actual value is yi, then ei is equal to y hat I minus yi, and its square is simply squaring this predicted minus actual. Okay, and then the total error will be nothing but sum over all these ei squares from the first training example to the nth training example or the total training example. So we are using this half just for mathematical convenience, and it has no physical significance as such. Okay, so the loss function is summation over all the squared errors, and then we are multiplying it with half for mathematical convenience. So if we write this error in form of vectors or matrices, we find the equation like this. So where a theta is nothing but the predicted values and y is the actual value. So error you are finding as square, right? So we already know, suppose we want to find square of a vector, what we do a dot a. So a dot a gives a transpose a, which is nothing but a square. So here a theta minus y is the error, and to get it square we do a theta minus y dot a theta minus y. So therefore this a theta minus y transpose a theta minus y is appearing.
So just
Okay.
one small doubt, sir, please.
Yeah.
This in the first lecture we were told that the loss function will be 1 by n, and the summation of I to I equal to 1 to n of E1 EI square.
Okay.
So that 1 by n is now got replaced by 1 by 2. I understand the mathematical convenience for that. But in that lecture, why was it given as 1 by n?
So it's okay. When you are using 1 by n, it will be called mean squared error.
Okay. Okay,
The
got it.
name will change. That's it.
Right.
I mean, the 1 by n will be also a scalar, right? So it has no significance as such.
Okay.
Okay. So next thing is to find the best theta. What we do whenever we want to find best things, I mean, when we want to minimize a particular loss. So in this case, our model will be best when the predicted values are close to the actual values, right? So that means we want to minimize the error. So the best set of parameters will be those which minimize the given error. So we do that by finding derivative and equating it to 0, right? So in this case, since it's a vector, we have to take gradient instead of derivative. So our grad of that vector should be equal to 0. Now, when we take the grad of this thing, this a theta minus y transpose a theta minus y, then we get a transpose a theta minus y equal to 0. And this detailed derivation has been done in week 4 live session. I think in first live session of week 4, we derived it in detail. So for revision session, I'm skipping that part. Okay, so you can refer to that live session and you will get how we did all these things. So from this, we are getting theta equal a transpose a. So simply see, when you are doing this del E equal to 0, you are getting this particular equation. Okay, so the A transpose which you had doubt is coming from this equation basically. So you, as you were in week 3, you people were mentioning how this A transpose is coming. So it is coming from this equation. So when you are taking del E equal to 0. Okay, and then from this equation, we can find theta as A transpose A inverse A transpose Y. Okay, so derivations, I think we did. If you people were present in week 4 live sessions, so you will know this. Next concept covered in week 4 was maximum likelihood. So in simple terms, how can we understand maximum likelihood? So see this figure. Suppose this is a figure where x-axis is some feature value x and y-axis is some label y. So can you tell me, out of these three lines A, B, C, which line is most likely to represent data points, which is given in this figure?
Line A.
A, right? Not B and C. Correct. So I can say A is most likely to contain all these data points, or I can say that this is the line of maximum likelihood. Correct. So this is what we say. So this is the line of maximum likelihood. Now, can you tell me, the second question is, how were we finding these lines? This line A, how were we finding it? If we were, when we were not knowing maximum likelihood, how were we finding it? Using least square, right?
Least squares, yeah.
Correct. So we can say that increasing likelihood or maximizing likelihood is similar to reducing the squared error or doing least square. So that is what is the concept covered in that particular part. Okay, so you can understand that from the mathematical equation which sir has given or from this simple example. Next thing covered in the first lecture is polynomial regression. So see, for some cases our data point is such that linear regression doesn't suffices our need. So data point may be like this. So here we need some non-linear model, okay, to represent our data. So for such cases we go for polynomial regression. So what we do, we basically transform our feature in the data set to get our polynomial equation. So for example, I have one feature in the data set. Let me call it x1. Then the possible models that I can build is by using the feature itself, right? As we were doing this, y equal to c plus mx1, right? So c plus mx1. So this was a linear model, right? So for this case, I only need 1 and x1. So now suppose I want to model a system like this, a plus b x1 plus c x1 square. Then I would require x1 square also, right? So what I'm doing, I'm just transforming this x1 to x1 square. So this is what we do in polynomial regression. Now suppose we have two features. Then all the possible combinations that we can have is 1 x1 x2, 1 x1 square x2 square, or 1 x1 x2 x1 square x2 square. So this basically depends on the model that you want to form. So suppose you want to form a model like this, theta naught plus theta 1 x1 plus theta 2 x1 square. Then you take this transformation. If you want to form a more complicated model, then you take this transformation. Okay, so it basically depends on the model that you want to form. So this is what is there in the polynomial regression. And I think we also covered this in week 4 live sessions in detail. So for now, you can understand the model will be given, and according to that, you have to take questions. So, okay. And you can refer to the tutorial also for solution of model of this form. Okay, that is also important in exam point of view. Now, next thing is regularization. So in layman term, what is regularization? It is nothing but to reduce sensitivity or the wide variation of output with respect to the input. So suppose we have two lines like this, A and B, okay? And now suppose my input changes from X1 to X2. So can you tell me which line is more sensitive to change in input?
Line A.
Line A, right? Why?
Slope is high.
Yeah, slope is.
Its slope is higher, right? So it is more steeper. So if there is a small change in input, there will be a larger change in output, right? So basically in regularization, what we are doing, we are playing with the slope. So if somehow we reduce this slope, then this sensitivity will reduce. So that is what we are doing in case of regularization. Okay. So the next thing which I was asked a lot in even live session was this. So in one of the expressions, sir has written A transpose A plus lambda I is invertible even if A transpose A is not. So can you tell me when a given matrix will not be invertible?
If it is singular matrix.
Yeah, so singular means its determinant is 0, and determinant is 0 when?
when it is not full rank.
Yeah, not full rank, it means its columns are not independent, right? Or its rows are not independent. So now, so suppose I take a matrix A transpose A, which is like this: 1, 2, 3, 3, 5, 8, 4, 7, 11. Okay. Now, if you see, the first column and the second column are independent, but the third column is nothing but the sum of first and second. So you can see this third column is dependent on first and second, right? It means this A transpose A is not invertible, correct? Because rank will be less than 3.
Sir, but A transpose A will always be symmetric, right?
Yeah, so I mean, I have just taken an example right here. So if A transpose A is not invertible, so consider this: if A transpose A is not, you can take a symmetric matrix, for instance.
But A transpose A will always be symmetric, isn't it?
So it won't be symmetric as such, because we when we were finding least square solutions also, I think A transpose A was not symmetric. Was it?
Yes, sir, it is always symmetric.
Can you tell this point?
Yeah, even if the matrix is not symmetric, when you multiply two, if A is not symmetric, or rather if A is not an n by n matrix, even at that time ATA will always be symmetric.
It will be square.
I mean, that is a property of ATA.
Yeah, okay, it will be a square matrix, that's for sure. Hello, Amrita ma'am, are you there?
Yeah, Vinandan, A transpose A will be symmetric only, right?
Okay, so A transpose A will be symmetric. Okay, I got a confirmation.
The matrix, when you multiply the transpose with the matrix, you will get a symmetric matrix.
Okay, fine. So this will be a symmetric matrix. So okay, consider this to be a symmetric matrix only. So we can change the terms maybe. Let me call here 2. Here it will be 3. Okay. This will be something like this, 7. Okay. So okay, now it is a symmetric matrix, right? And this will be 10. Correct. Again, the same condition holds, right? Now this third column is the sum of first 2 columns, correct? So it means A transpose A is not invertible. Okay. Now, even if A transpose A is not invertible, you are adding A transpose A to 2i, right? So what is happening? When you are doing that, what is happening? The first element, instead of 1, it has become 3. This has become 7. And this will become 12 in this case now. Okay. And this remains 7. This is 3. This is 2. Okay. So see what is happening. We are simply removing the dependency between different columns. So when the dependency is removed, it means A transpose A plus 2i becomes full rank. And if it becomes full rank, it means it will be invertible. So even if A transpose A was not invertible, A transpose A plus 2i will become invertible.
So, but how can you say that always this dependency is removed?
So it is removed because we are adding something to only one of the elements, right? Not to all the elements of a column. So in the first column, you are adding to the first. In the second column, you are adding to the second. And in the third column, you are adding to the third. Not to all, right?
So in this case, even we add a epsilon to each of the diagonal element, then also technically you can make the matrix invertible. Because the dependency
any value. Therefore, it is lambda, right?
Right.
So you can take any lambda value.
Yeah.
So in any case, you are just removing the dependency between the columns, and therefore this whole matrix becomes full rank. So it will always happen. Devansh, I think you asked this. It will always happen. Okay. So the next lecture was on eigenvalues and eigenvectors. So basically, whenever you apply a linear transformation on a given vector, then what happens? Suppose this happens after you apply a linear transformation and you get the equation like this: ax equal to lambda x. where X is the vector on which you are applying the transformation, lambda is a scalar, and A is a matrix or the linear transformation matrix, then we say X is the eigenvector of A. Okay. So what it means X has not changed its direction. It is remaining in its basis. It is only getting stretched or shrinked. So this is what is the concept of eigenvalues and eigenvectors. So in this case, lambda will be called eigenvalue and X will be called eigenvector. Okay, of A. And I think we covered this part in tutorial, so you can refer to that. And the motivation that sir has used, the differential equation part, that also we covered in detail in one of the live sessions. I think second live session of week 4 we covered it, so you can refer to it in the first half. We have derived it completely. Now next important part is how to find eigenvalues. So to find eigenvalues, we'll be doing A minus lambda I, its determinant you'll take, and you'll equate it to 0 to find eigenvalues. And to find eigenvectors, you'll be using Ax equal to lambda x. So this is also important in exam point of view. Next concept was diagonalization. So we derived, again, we did the derivation in live session. So for this revision, I will only tell you the steps that we do for diagonalization. So first step is you have to find the eigenvalues. So whenever a matrix is given, suppose a 3 cross 3 matrix is given. So this is for 3 cross 3 or in general, any n cross n. What you have to do, you have to find the eigenvalues. So suppose in case of 3 cross 3, you get 3 eigenvalues, which are lambda 1, lambda 2, lambda 3. Now you will find the eigenvectors corresponding to each eigenvalue. Okay. Okay. Now what you will do, you will find a matrix S. So S will contain all the eigenvectors in each of the columns. Okay. So you will just tag these x1, x2, x3 as the columns of S. Next thing is the last step. You will simply write S inverse AS equal to lambda. This capital lambda is nothing but this. It contains all the eigenvalues along the principal diagonal, and rest of the elements will be 0. So you have to just keep in mind, suppose you keep x1 as the first column in this matrix S, then you have to write lambda 1 as the first element of the first column. X2, then you have to write lambda 2 here. X3, then you have to write lambda 3 here. If you interchange this, so your eigenvalues will also interchange according to that. So that thing you have to keep in mind. Okay. Now one important property that sir has covered in the lecture. So suppose we have a diagonal matrix which we obtain like this, S inverse AS. Let us call it equation 1. Then suppose I multiply equation 1 with equation 1 itself. Then what I am getting S inverse AS into S inverse AS, which is nothing but this capital lambda square. Okay, why is it so? Because this S into S inverse becomes I, then A remains, which is A square. So similarly, if we multiply this equation 1 k times, then we get S inverse A to the power k and S. Okay, so this is what about the diagonalization part. So these steps you should keep in mind. This step 1, 2, 3, and 4. So this, so you can diagonalize any given matrix if you have sufficient number of independent eigenvectors by using these methods. Okay. Okay. So for next lecture, which is Fibonacci sequence, it was also all the things were derived completely in live session. And it is not as important from our exam point of view because it is one of the applications of diagonalization. So you can see through this lecture only. So it is not that important from exam point of view. So the last lecture of week 4 contains orthogonally diagonalizable matrices. So suppose now see this orthogonally diagonalizable matrices are special case of diagonalization. So it happens when A is real symmetric. So we know that S inverse AS equal to lambda in normal square matrices case. So we can write A equal to S lambda S inverse. Now for a real symmetric case, what happens? S holds another property. So S, what property S does have in case of real symmetric? S transpose equal to S transpose S, which is equal to I. So hello, was I on mute?
So for
Few
Few
seconds.
seconds.
Yeah, okay, sorry. So this S transpose equal to S transpose S is equal to I. So if there is a matrix like this, then we call that matrix as orthogonal, right? So here S is orthogonal in case of A, if A is real symmetric. Okay, so we can write in place of S inverse, we can write S transpose, correct? For our orthogonal matrix, S transpose equal to S inverse. So we are writing S transpose in place of S inverse, AS equal to lambda. So sir has called this matrix as Q. So the expression is A equal to Q capital lambda Q transpose. Okay. Okay, what are the steps involved? Again, the steps are find the eigenvalues, then find corresponding eigenvectors. Okay, the additional step that you have to do is normalize the eigenvectors. Why you normalize? To get this particular expression. So if you don't normalize, you will not get this I. So you have to normalize the given eigenvectors. So how will you normalize a given eigenvector? You have to divide it by its length or its magnitude. So in that way, you normalize a given eigenvectors, and the rest of the steps are same as in case of normal diagonalization. So that's it in week 4. So any doubt, you can please go ahead.
Sir, I have a doubt that S is always unique. It was given that S is always unique, but
no, S is not always unique.
Okay.
S is not unique. I mean, we have discussed this thing also. So S is not unique because these eigenvectors are not going to be unique. If you multiply an eigenvector with some scalar, it is again an eigenvector.
Okay, and what about lambda, sir? Lambda should also not be unique.
No, eigenvalues are going to be unique.
No, sir. This matrix. I'm talking about the matrix.
S, okay, yeah. So S will be not unique, but this lambda will be unique since these lambda 1, lambda 2, lambda 3 are going to be unique.
Sir, but if we change the S arrangement of x1 and x2, then the lambda 1 and lambda 2 will be changed and in the arrangement, right?
Okay, so for a given arrangement, it is going to be unique. I mean, if you take x1, x2, x3, then it will be always lambda 1, lambda 2, lambda 3.
Okay. For a given arrangement.
Yeah, so if you take x2 here, it will be lambda 2, lambda 1, lambda 3. So in that arrangement, this will be unique. So basically, you have to keep in mind that eigenvalues are always going to be unique and eigenvectors are not unique.
Okay.
Sir, here S, does that have to be always like full rank? Or like in the previous example, we saw it was not.
So S is always going to be full rank. Why? Because x1, x2, x3 are going to be independent.
But if it's not full rank, then there won't
Then
be
we
like
cannot
enough.
diagonalize.
So that like I think that should be mentioned too, right? Because while doing some examples on your own, sometimes it turns out to be I think not non-invertible.
So it's great that you have arrived at a conclusion, right, by doing yourself.
But like it should be mentioned in the definition of diagonalization.
Yeah, so it
like
is indirectly mentioned. It is indirectly mentioned since we are saying when the eigenvalues are unique, x1, x2, x3 are independent, correct? So when x1, x2, x3 are independent, and when you are stacking them together, then this matrix is going to be full rank, correct? So I think it doesn't require any special mention. So I think I'm clear on this part.
Sir, Sir, can you please explain step 4, how you got capital lambda as this matrix?
Yeah, okay. So this derivation we have already done in live session. So
no, sir, no, sir,
if you...
I am not asking derivation, but sir, you have found out you have written capital lambda, no, sir. How you got this capital lambda matrix? Can you explain this?
So
how you write this?
Yeah. So again, this comes from this derivation only. I mean, when you do this.
No, but sir,
that
previous live
is a
session
property.
you have not.
No, property. Yeah, it's fine. It's a property. But okay, you can take any matrix. For instance, you take a matrix like this: A equal to 1, 2, 0, 3. Okay. Now can you
Yes.
tell me what are its eigenvalues?
So 1, 3.
Okay. So lambda 1 will be 1 and lambda 2 will be equal to 3.
3.
Correct. Now
Yes.
let's find the eigenvectors. So for lambda 1 equal to 1, how will you find eigenvectors? You'll find it using a minus lambda I x equal to 0, correct?
0. Yes, sir. Yeah.
So you will doing 1 minus 1, 2, 0, then 3 minus 1, correct?
2. Yes, sir. Yeah.
x1, x2 equal to 0.
Yes.
So from this you will be finding the eigenvector, whatever is the eigenvector. So what will be the eigenvector in this case?
So this is your x2, x2,
1, 0.
0.
So x2 equal to 0. So your eigenvector will be something k0. K0 form. Okay. So k you can take any value. So it will be equal to 1, 0. If I take k equal to 1, then it will be 1, 0. Okay.
Yes,
next for lambda 2 equal to 3. 3 was there, right? So the equation becomes
yes.
minus 2, 2, 0, 0. Correct?
Yes, sir.
Yeah. x1, x2. This equal to
0, 0.
So minus 2x1 plus 2x2 equal to 0 or x1 equal to x2. So v2 becomes 1, 1.
Yes, sir. Yeah.
Correct. Now how will I form s? S will be nothing but 1, 0, 1, 1. Okay.
Okay, sir. Yes.
Okay. Now you find S inverse, whatever is the S inverse. So can you find it?
Sir.
It is?
Yes, sir. Yeah.
If you remember this, the shortcut.
Minus.
So if you have a 2 cross 2 matrix like this, A, B, C, D, and if you want to find its inverse, then you do this 1 AD minus BC.
BC, yes, sir.
Then you interchange these two. I don't remember which two you interchange. I think you interchange
the diagonal you interchange.
D and A, right?
Yes, sir. D.
Signs,
and
reverse
BC
sign.
remains same, right?
No,
or with some negative
sign
sign.
will change. Sir.
Yeah. So this negative sign, right?
Yes, sir. Yes.
Yeah. So you do like that. So it will be 1, 1 minus 0, and then interchange this. So 1, 1 remains same. It will become minus 1, and this becomes 0, right?
Yeah. Yes, sir.
So this is 1 minus 1, 0, 1. So I'm assuming we have calculated inverse correctly. Now, if you do this S inverse AS, okay. So you put this 1 minus 1, 0, 1, and then do A. A was 1, 2, 0, 3, correct?
Yes, yes, sir.
And S was 1, 1, 0, 1, correct?
Yes.
Now, if you do all this multiplication, I am assuming this inverse is correct, then you will get this. You will get 1, 0, 0, 3.
1, sir, na? 0, 1, 1, 3, 1, 0, 0, 1 होगा ना सर? This will be, I think.
नहीं 1, 1, 0, 0, 3 होगा. क्योंकि यहाँ पे आइगन वैल्यूज क्या है आपके 1 और 3.
Okay, yes, sir. Yes, yes, sir.
Okay.
Okay, sir. Thank you.
Yeah. Okay.
So, is there any short method for 3 cross 3 matrix to inverse?
So I don't know. I mean, if anyone from our team knows, I don't know any shortcut for that. So you have to go for this 1 upon determinant A, then adjoint A. This always works.
This is very time taking.
Yeah, this is time taking, but with practice it becomes easy.
Gaussian elimination can't be just.
So Gaussian elimination, I think it takes more time. If you are doing that and then you are finding this, if I'm not wrong, you are doing this A inverse equal to I, right? You are making this side equal to I in Gaussian elimination. So it takes more time, I guess.
Sir, I have one question. Like whenever the diagonalized matrix will be given with the eigenvalues, always will it be given in the matrix format? or just
Yeah,
with the
so
value?
whenever diagonalization is asked, most of the times it will be in matrix format.
Okay. Okay, sir. Thank you. And sir, apart from this, I have one question from the first concept you have explained, like mean squared something. So I think the mock question 14. If you, it would be great if you can explain in little bit detail.
Okay, so I think I have to open that question. So give me a minute. So till then, if you have any other doubt, you may ask from our team or me.
Sir, the first lecture you mentioned the sum square. Can you explain that part?
Sum square.
Yeah.
You mean the error part, right?
Yes, error part.
Okay. So now suppose this was the table that I had got for income, right? Now suppose from the prediction, if I from the model I am getting a prediction of income like this: 1 0 0 100. I am getting 1 49 0 0 2 0 1 whatever. From the model I have got this value. Okay. Now what will be error? Error will be nothing but subtract from this. So you will be getting even. The first error will be 100 100 minus 100 000. So which will be nothing but 100. Second will be E2, which is again the subtraction of these two. So I think it will be 1000. E3 will be subtraction of these two. So not 1000, 10,000. And here it will be 1000. Okay. Now what is sum squared error? You have to just square these things. So you have to do 100 square plus 10,000 square plus 1000 square. So whatever is the value, 100 and 0 plus 1 0 and then 4 zeros again and plus. So whatever is the sum, you get some 1 0 1 0 0 1 0 something like this. This is the error that you are getting. This is a squared error. Now, if you want to find mean squared error, then what you will do? You will divide it by the length. So you will divide 1 by 3. And if you are using sum squared error, you will do half into E. I hope it clears how to find error.
Yes, sir.
Yeah, okay. Okay, any further doubt?
When we will get these live session sheets?
Live session?
I mean, these sheets, these workouts.
Okay. Oh, you mean this the lecture slides that we have covered in revision?
Yes, yes.
Okay. So Anamika ma'am, can you comment on that?
I think we can add it in that supplementary contents of the portal. There is, to find the PPT or slides folder, right, in the portal. We will add it today.
Okay.
Yeah.
Fine. So we'll add it. Which question number 14 of mock you had doubt, right?
Yes, sir.
Okay, so let me open that. So any other doubt? Can you ask me? I'm having some issues with logging in.
छोटा हो चुका है.
Can you solve one second degree polynomial? Abhinandan sir?
Yeah, sure, I'll do that. So I have opened this mock. Let me first do that. So mock unit, quiz 1. So question number 14, right? 7, 8, 9, 10, 11. Okay, so consider a line with 0 slope, y-intercept of 2. The sum of squared residuals obtained when the line is used to fit the following data set is. Okay. So I think we have covered this in Solve with Instructor of week 3. Very similar question. I think we have covered it. So anyhow, I will give you an idea for this.
Okay.
So,
sir,
if
is there
Amrita
in
ma'am,
that
if you
question, is there any I mean PA or G? I don't think so. Similar question was there.
Yeah, so in Solve with Instructor, we have covered a very similar question.
Hello?
So ma'am, if you want to take it, or shall I proceed?
For this question.
So question number 14, it's consider a line with 0 slope and y-intercept 2.
Yes, yes.
The sum squared residual obtained when the line is used to fit the following data set.
Okay. So do they want us to solve or explanation is in it?
Okay, so maybe explanation will be fine, right?
Yes.
Okay, so
okay.
Will you
So
take
for
it,
this
or?
question, see, yeah, I'll take it a minute. Simple, right? For this, so you are given a data set with x and y. So here your x is your independent variable. So y is your dependent variable for which we are going to find the model. So you are given that the model is a line which has 0 slope and y-intercept equal to 2. So therefore, your line equation will be what? Y is equal to mx plus c. Here m is equal to 0. That is slope to 0. So your y-intercept is 2. So therefore, your new line will be y hat equal to simply 2. So you are asked to find the sum of squared residuals. So what is the residual? The residual is the error from y hat and y. So that is y hat minus y. So you find this, you add one more column here, which is y hat. And this y hat is simply equal
Ma'am, is
to
it possible for you to just write little bit because I'm
Okay,
not
okay,
able to.
I'll do that.
You
Whatever
want to
ma'am is
write?
saying, I'll do that.
Okay, ma'am. So can you? We cannot write it in this sheet. It's in you. Okay, you can write.
Yeah.
Yeah, so your slope is 0 and the axis is 2. So you have this x and y. So x you have, and you can draw a table with x and y. You can write y as y hat as 2. Y hat is equal to 2. Yeah, that's it. So your x values are to refer from that question.
X values are 1, 2, 3, 4.
Okay, x is 1, 2, 3, 4. And y?
2, 4, 1, 3.
2, 4, 1, 3. Okay. So your y is only 2 for all the entries. 2, 2, 2. So now your residual value is what? Your residual value is y hat minus y. So that is your residual. So
here for loss, don't we take like 1 by n?
No, that is not loss here. That is something related to your regression loss. No? So this is simply given as find the sum of squared residuals. So residuals are nothing but the difference between your model and the given y value. So that is the residual term in least squares method.
Okay.
Is this in which week, ma'am? If I have missed
It is
something.
third week.
In third week, okay.
Yeah. So you have this residual value, right? So y hat minus y. So your sum of squared residuals, that is this, you have to square this residual value, that is y hat minus y squared, and then sum them. That is it.
Okay, got it.
Yeah.
But
So it is
here,
6.
here, ma'am, sir had just explained sum of squared residuals would be divided by 2.
Yeah, that is sum of squared error, right? Here we do not consider this residual as error.
Okay.
Yeah, it is simply you just take this residual as your some prediction minus your target, that is original value.
Yeah, so
that is
maybe
the simple residual.
in this example, we can say sum of residual will be equal to 6, as ma'am said. Sum squared error will be 6 by 2, and mean squared error will be 6 by 4.
Yeah, sum of squared residuals.
Now it's clear. Yeah.
Because this residual term is related to that least squares approximation method. So there they call it as residual.
Right. Now it's clear, ma'am. Thank you.
Yeah.
So in sum of square, every time we need to divide by 2, sir?
Yeah, it is sum of squared error, right? We call it as
Yes.
error.
Okay.
At that time, you divide it by 2.
So any other
Any other
doubt?
question?
So if there are no further doubts, we may close the session, right?
Sir, one question. Like if suppose the eigenvalues are given and we need to write the diagonal matrix. So how can we assign lambda 1, lambda 2 and lambda 3
So
into
the
that?
general practice is from greater to the smaller.
Okay. So lambda 1 will be the greater value.
Yeah.
Suppose
Greater
2,
to
3,
smaller.
5 is given. 2, 3, 5 has given. Then 5 will be lambda 1, 3 will be lambda 2 and like that.
Yeah, so it's like that, but it's not a hard and fast rule.
Okay. Yeah, okay, sir. Thank you.
Thanks a lot. Any other doubt?
None from my side, sir.
Okay, so I think we can say wish you all the best for the quiz.
Thank you, sir.
Yeah.
Thank you, sir.
Do well.
Thank you, sir. All the
Thank you,
best,
sir.
all of you.
Yeah, thanks for all of your participations.
Thank you all.
Abhinandan sir, can you please
Yeah.
solve one second degree polynomial?
Yeah, okay. Sorry, I forgot that. Yeah, okay. So suppose I have feature x1 and I have to do a second degree model fit, okay? Now, suppose my model that I choose to fit is like this. Okay. Now, suppose the data given is like this, y and x. So suppose x given is 1, 2, 4. Corresponding y's are 4, 16, 19. Then can I write y1? Similarly, y2. Okay, so where y1, y2, y3 are the given values here, and x1, x2, x3 are the given values here. Okay, so I can write this equation simply as like this. So 4 equal to theta naught plus put the values of x1. It will be theta 1 plus 1 square. That is theta 2. This next will be 16 equal to theta naught plus theta 1 into x2, which is 2 theta 1 plus 4 theta 2. And 19 will be equal to theta naught plus 4 theta 1 plus 16 theta 2, correct? So I can write it as in matrix form as 4, 16, 19 equal to, with theta naught what we have, 1, 1, 1. With theta 1 we have, okay. So more compact notation we can give. We can simply write it like this: 1, 1, 1, then 1, 2, 4, next 1, 4, 16, whole into theta naught, theta 1, theta 2. Now what will be theta naught, theta 1, theta 2? It will be simply equal to 1, 1, 1, 1, 2, 4, 1, 4, 16, inverse, and then 4, 16, 19. So whatever is the value is your answer. Okay?
Okay, sir. Thank you.
Yeah, most welcome. So any other further doubt? Okay, so I think we can close the session. Again, all the best, all of you. Bye.
Thank you, sir.
Thank you, sir. Thank you, ma'am.
Thank you.
Thank you, all of you.